Bhopal to the participants.
So, good afternoon to one and all. It's a great privilege to introduce our today's chief guest, Dr. Anvesh Kumar Naila. So he is currently working as an assistant professor in the School of EEE, VIT Bhopal University, Bhopal, Madhya Pradesh, India. He has pursued PhD in the Department of ECE, VNIT Nagpur in 2019. He is having 3 years of teaching and research experience. He has published his research and review articles in 17 SAE and SAE, 3 Scoopus, 5 in international and national journals, and 16 international and international conference. He has edited 3 textbooks published by Springers in 2021-22. He also an active research consultant for several funded projects. His research interest includes antennas, RF circuits, and wireless communication. He is working in the area of plasmonic observer and metamaterials. His directional UWB antennas, reconfigurable antennas, cognitive radio antennas, RF energy harvesting, and terahertz and mobile antennas. He is also an active reviewer for various IEEE and IET, elsewhere, and Springer journals. Thank you so much for introducing today's chief guest.
Yes, I don't know, Virendra Singh, you are not audible to us. Maybe I could able to hear from Shiva Prasad sir and then Shravan, I guess. Yes. Okay.
Not audible. Still, Virendra, you are not audible. Okay, sir.
Yeah.
Thank you very much, sir. Anvesh sir, for accepting as a resource person today. You can take off, sir.
It's my privilege, sir. It's my privilege to accept that.
Sir, you can take off, sir. No issue. You can take off.
Okay.
Sultan, please give screen share. Sultan.
Yeah, I could not able to share my screen actually.
Sultan, please give sharing.
Given, sir.
Okay.
Please check it now, sir.
Yes, I will just. Yes, I could able to share my screen. Yeah. So let me share my presentation so that. I believe the presentation is visible to everyone. Sir, please confirm Shiva Prasad sir so that I can proceed further.
Very much visible, sir.
Okay, okay. Thanks for the confirmation. And first of all, I should say thanks for the invitation by Dr. Virendra Singh. And then thanks for the introduction with me about me related to my research and all. So I think I'll just basically I just want to interact with the scholars and the researchers. So what I have experienced in the domain of antennas, then maybe ultra wideband terahertz. First of all, I'll just assume that the fundamentals of antennas, in the sense like what is antenna, then how the performance of antennas is like measured, like maybe a reflection coefficient or maybe gain, then directivity, radiation efficiency, because those are the terms I'll be using in my work regularly. So I'm in between, like if you have some queries like, sir, how this is happening and that is happening, such kind of things maybe we can discuss. In fact, I'll just interact with all these scholars and faculties, so that we'll share the experience. It is not like I'm just delivering something and then just you listen it. I'll just ensure that you all get some techniques to design several antennas. Okay. Yeah, we have several techniques in the literature, but just we had come up with several structures which may be something new to the community, antenna community or RF community. That is what I'm just going to share, because this is my personal experience, and then the work which our team has done it. Yes, so ultimately the concept is that directional planar antennas for ultra wideband and terahertz technology. Yes, the statement is simple, and you may be wondering, like, sir, we have been listening this directional antennas for ultra wideband and terahertz technology since a long time, but what is new? Yes, that is what I'm just going to share. Yes, in the literature we have several antennas, but what is something new in our design or maybe in our prototype for ultra wideband and terahertz technology? Okay, the sample directional property of a 3D radiation pattern we call, that is what I have shown in this thing. It may not be new to us, to the community, antenna community, but whenever I show the structure, then you may feel that the structure is something new or maybe something different, because let us have a discussion over it, because it would be a good and good learning with the new structure. This is my just okay, let me just check. Yeah, okay, this is my just profile. I just put my research areas, publications and all. It is not just to show that what I have published or what I just want to connect with the community. So I just want to connect with antenna community. That's why I accepted the invitation, and then that's why I'm just sharing my profile, and then even I to have here my mail ID or contact number, so that it is not like we collaborate. I know my point is like I'm ready for collaboration, and even I have just mentioned my research areas also. Apart from publications and all, I need not to mention that because okay, everybody will publish papers and all, but I'm just my point is I'm ready to connect with people and then ready to collaborate with anyone. And my area of research is that and we are working, our team, we to have scholars, then we have collaborators from several IITs, NITs, then several DRDO branches like RCI, then IST, NITs and all. And my research includes basically planar antennas, then reconfigurable antennas, and something new to us is little RF energy harvesting. Yes, we to have listened this term RF energy harvesting. Our team is working. One scholar with me, he's working in RF energy harvesting. Then he's also looking into RF circuit design, and then another scholar who is working in microwave imaging. And then we to have some student power to work in plasmonic observers. Okay, so that is what we discuss maybe later on in some other time with you guys. But this is just my profile and all my interests. Okay, just to connect with you, not to say anything else. And shallow. So then the main motive or like main objective of my this interaction, I should say, that I'll just let you know guys with the several techniques, new techniques, not already whatever we have techniques studied related to directional antennas. Okay, so the title is very interesting because you too have listened some ultra wideband antennas, directional ultra wideband antennas, I should say, maybe Vivaldi antennas, Vivaldi or Vivaldi we say. And then you may have heard about helical antennas, wire antennas. Then you might have heard about conical antennas. Then Yagi wood antenna, it's a narrowband antenna, but it is a good directional antenna which we could have seen in our olden days. Okay, then conical antennas, biconical antennas, bow tie antennas, and all those things, some kind of directional antennas, non-directional, omnidirectional, or all wideband antennas, all those we have listened in the literature, but we'll just come up with some kind of new. And here first I'll take on ultra wideband technology. Yes, basically the standard of ultra wideband, you know that if something is fractional bandwidth, more than 20%, we believe that. Okay, and then okay, anyway, it's ranges from terahertz range, gigahertz range, megahertz range, but mostly fractional bandwidth of 20% is considered to be ultra wideband, and then if you consider absolute bandwidth, then it is treated to be 500 megahertz. Okay, that is the point. Just let me take up my marker so that sometimes maybe I'll just surround. I'll just take on this ultra wideband technology first. Then we'll see about terahertz technology later on. And the term ultra wideband means, that is what I said, 20% fractional bandwidth, and then maybe 500 megahertz of absolute bandwidth, and then a very popular band proposed by FCC. Okay, it is from 3.1 to 10.6 gigahertz. Since it has crossed more than 500 megahertz, it is treated to be ultra wideband. It does not mean that ultra wideband is only 3.1 to 10.6. Many of the times we had come across that people, the moment we say ultra wideband means, they say only 3.1 to 10.6. It is because the bandwidth is crossing more than 500 megahertz. That is why it is treated to be ultra wideband. Otherwise, everything can be called ultra wideband if it is crossing the limitations. And another point, but since in 2001, the US, they are for their purpose, or maybe all over the world, in fact, there are certain countries who had unlicensed a band 3.1 to 10.6. So from that time onwards, there are plenty of publications, like they say ultra wideband antennas, reconfigurable antennas, then integrated antennas, ultra wideband, narrowband. That kind of technology is emerging. Still there are so many publications on this concept of ultra wideband 3.1. People are proposing planar antennas, then that other directional, omnidirectional, reconfigurable. Many flavors are coming actually. Okay. So that is what I'll show here. Also, my interest is that propose a novel technique for ultra wideband technology, and that too, what I expect is that it should be directional. That is what my intention. Okay, for main focus is from 3.1 to 10.6, and then okay, and I'll just highlight another thing, like we could have seen several antennas, like spherical dipoles. If you look at the second statement, we have some triangular dipoles, bow tie dipoles, then biconical dipoles, or some other antennas were proposed for these ultra wideband applications. So the main purpose of them is you can use them in ground penetrating radar, then imaging applications, vehicular radars, wireless body area network, wireless personal area network, then through wall radar imaging surveillance system. So in this specifically, if you consider this ground penetrating radar or radar imaging, or maybe some other concepts, if you look at, then in those places we expect directional antennas, because a ground penetrating radar, in such case, like you expect, what you expect is that the beam needs to be directive, then only the things, the radiation beam will go to a particular target, then only it will come back. So in that case, if you have like isotropic or omnidirectional kind of structure, then there is no point. So these are the several applications like ground penetrating radar, radar imaging, and all. That's a reason our motivation to design a simple compact. So my motivation is to design a simple compact directional ultra wideband antenna with suitable characteristics. So this is my motivation. And then here you can see you have this one helical antenna. So here you have, it is a wire antenna, and then you can see this is Yagi-Uda antenna. This is what I was talking about, planar Vivaldi antenna. So this is what about literature. Now my goal is to come up with the structure which is different from these structures. So whether it may be helical antenna, or maybe agate antenna, or maybe Vivaldi antenna. That is what the challenging thing. Okay, so then in this case, if you look at this one, this is my structure what we have proposed for directional property. Okay, so point is I should get my complete ultra wideband 3.1 to 10.6. At the same time, I should not compromise on the directional property. And really, I just want to say there would be many learnings here. There would be many learnings, so that one can look into these learnings, and then they can use these concepts in their designs, in the design of antennas and all. For me, this structure might have taken much time, but I just understood many things. Okay, so I'll just put up a few points so that people can learn by doing what activity, what is the thing happening, so that we'll just get the advantage of this presentation. Okay, first of all, I'll just want to show this one, this circle slot. Okay, so it is under the feed line. First point, I just want to conclude here that if you put a slot under the feed line, then it enhances your impedance bandwidth. Okay, so if you put a slot under the feed line, then it enhances bandwidth. And another point, what we know is in the Aguda antenna, we have a habit of putting director elements, but here we put director elements on the top and bottom plane. Now, if you look at this fabricated prototype, you have this top elements and director elements. Obviously, one can easily understand that it is just used for directional property. So here we have that kind of thing. Now, again, I just want to show here about feed line. Now, it is not your center feed line. Okay, it is absolutely offset feed kind of structure. So this is what, from my study in the antennas, what I found is, by considering offset feed to any structure you take, whether it's a any structure, any planar structure, but if you go with offset feed mechanism, then definitely it will give you directional property. Even I'll show you the results whenever you consider center feed and then offset feed, then what exactly happening about directional property. Yeah, yes, one will change, reflection coefficient will change, but here the focus, or maybe some new learning for me is that by putting offset field, what exactly I get directional property. And this many people may be knowing, may not be knowing, that's what I'm just sharing. And then another thing, like you have here notch. People know, many other times the community knows that by putting a notch on the top layer, then we'll be having a additional resonance. So this is what we had come across many times in the literature, that whenever you have a notch on the top layer, then it will create another resonance actually. So we'll just, whenever you want notch bands, then we use this one. Yes, here also same thing, the slots whatever I put in the L shape, they are creating additional resonance. That maybe I'll be showing next. Another thing, I just have used this flared structure. If you look at on the left and right, and the two top and bottom, not only on the top or bottom. If you see here, then this is on the left side, right side. So again, yes, whenever I use offset feed, then it's not exactly, yeah, we'll get directional properties, but it is not up to that directional what we expect. So in order to get complete directional performance, I have used these flaring structures on the top layer and bottom layer. If you look at here in the bottom layer also, like this is what the bottom layer, and it gives me complete directional properties. So for me to learn these points and all, it has taken so much time. But anyway, I have learned so many points from this one. You introduce slot on the ground for enhancing bandwidth, then offset feed for directional performance. Then you put a slot on the top layer to get some kind of resonance shift, and then flaring structures that can be used for improving the directional performance. Now, here you can easily understand that this is my 10 dB limit, and then you can see this is my lower cutoff, and then this is my higher cutoff. So it goes from that dash one is simulated, which is coming around approximately 3 gigahertz to 12.5 gigahertz. So it is almost good because my focus is on 3.1 to 10.6. So it's completely covering. Okay, so mainly another thing, you can see that this is the ground plane whatever we have used. It's a partial ground structure. Partial ground in the sense, this is very well known to us that if you adopt a partial ground, then definitely it will create us ultra wideband. That is the easiest technique which we know already. Then this is another point where you can see S11 is and the limits, and then this is what on the figure 5 you can see, which is your peak gain. Now you can see that the directivity is, as frequency is increasing, that my directivity is increasing. Okay, so that is you can see that may be due to the reason that as frequency increases, then your wavelength decreases, then the more aperture area, that might be the reason for gain. Many other times we do get confused, like why the gain is increasing from low frequency to high frequency. The reason is that as frequency increases, then wavelength decreases, then aperture area or aperture area that increases, so that gain. And moreover, many of the times at lower frequencies you will find omnidirectional properties. Omnidirectional, then as frequency increases, then it goes to directional property. Okay, this is what the structure what we had. And then yes, now you can see here, so this figure, whatever it's in, okay, it's not exactly directional, but still it's fine. It is maintaining the directional property, but it is at 6.3 gigahertz. And then if you look at this one, it is exactly at 10.5 gigahertz. So just now I mentioned several points that as a frequency it is going upper, then it is becoming more directional. Now, why I'm happy with the structure is, one should say that, one may say that, sir, we to have Vivaldi structure, which is giving you a better directional property and at the same time ultra wideband. But here, what our point is, we had come up with a new technique to have directional. Either you use flaring structure, then offset feed mechanism. That is what I'm just always say that this would be something new for the literature and all. Okay, now I'll just see what are the steps we had followed. So everybody knows that we started with a simple planar structure. Now here, like, you'll understand what is the credit of each step. Okay, so first it is a simple planar structure, and then it is a partial ground. Then you to have some S11. It is showing like multi-band performance. It's okay. Like you may be getting 2 or 3 resonance. Okay, that's fine. Because there would be higher order modes, because of which you may get some resonance. This is simple planar structure. Then if you see here, I just want to show the credit of this adding slot over here. So if you see in this bottom layer, you have a ground slot, and if you look at the S11 performance, okay, on the right side you have whatever you have. Yeah. Now, if you compare these two structures, then you see first step, whatever I have just shown previously, it is just a multi resonant kind of behavior. But after introducing slot in the bottom layer, now you see the curve is something like this. Now this is what the solid line. Now, it is very clear that by adding that slot on the ground plane, it is enhancing your bandwidth. That is what I can conclude here. Next, now another point, next point. What is my next step? I just added offset feed. Now here it is center line. It is center line. Now I just added my offset feed, which is towards the end of this radiating structure, and then I maintain the same ground plane. Now here you see here there is some solid line. What is the result of your uh, offset feed? Okay, so if with the planar structure, if you look at this one, this curve, it is a simple planar structure without offset feed. And if you look at the corresponding curve, then it is presenting almost omnidirectional, because you people know, we know that simple planar structure gives us a figure of eight and then omnidirectional pattern. That is what we obtain. But what we can conclude here from the structure is that by just putting offset feet, then it is having some directional property. Now from these one can easily conclude, you take any structure, instead of center feed you put offset feed, then okay, you have to, you know, you have to, it's not like you just simply put offset then it gives you a simple directional property. No, you just have to maintain a particular length and width. So there won't be, there are not any mathematical, but still it is not possible to get directional properties by simply putting. Yeah, up to some extent you will get it. So this is what I can have. And remaining, you can see that that is not in case of planar structure center feet, you don't get uh, directional property, but whenever it comes to offset feet, yes, we are getting directional property. Then this is it, you know, this is what we have the frequency at 5.5 gigahertz. Then another point here, you can see here these two solid lines, like, you know, dash dotted, and then this solid line that gives me completely directional. Okay, so I just want to show this curve. This is one curve, and then you can see this curve. But the point is, in this, the complete solid one is pi equals to 90 degrees, and then another one is pi equals to 0 degrees. It means one is in YZ plane and one pattern is in XZ plane. Means we are getting directionality in two planes. One is in YZ plane, one is in XZ plane. Yes, by putting offset, yes, it is giving me directional property, but it is in XZ plane and YZ plane. So now to clear that, like, what is my focus? I just want my directional property towards YZ plane, because we want end fire radiation pattern, not this kind of pattern, because we don't want main lobes in multiple directions. We want my directionality in YZ plane. For that only we just added that flaring structure. So just I said here that step I might have not told, but the main purpose of these flares is that to limit your directional property in one plane. Okay, because you can here you'll understand that the directional property is in both planes, YZ plane and XZ plane. Now to clarify that, you can see here this proposed antenna. These are the curves, 2D radiation pattern curves, from which you can easily understand that I am getting my directional property along YZ plane. Okay, so this is XZ plane. If you look at here, dash double dot, so that is somewhere around here, this one. Okay, so this is dash double dot. By limiting my this one, what we call flare structure, by putting flare structure, one plane main lobe is completely diverted, and then you can see this, whatever this solid line, this solid line that is exactly towards YZ plane, and then dash dot that is in the, that is also in the YZ plane. That is how we have designed this structure. So there are some study or maybe some credit from the literature, because that slotted ground is not new concept. Okay, but flaring Yeah, that is what you see in Vivaldi, but it is not exactly flare. In Vivaldi also you use flares, but it is not exactly, we can say that it is a flared kind of structure and all. So here another advantage with this structure is it is compact. Whenever you go to Vivaldi, then it takes, larger dimensions, but ours antenna is, little compact. It's almost having 40 mm by 30 mm. It's an average dimension, and then you can see this is a conclusion of all steps. But here I just want to conclude one point here. If you observe uh, this one, monopole with offset feed. Yeah, I do understand it is clumsy, but here my point, I just want to conclude one point. Here why we put notch, this one slits here, this L shaped slits. I just want to show you the credit of this L shaped slits. So if you observe properly, this is whatever I have circled, uh, dash dot, and then this one offset feed. Here one curve, its lower cutoff frequency is somewhere else 4.5. So this is what the curve, whatever I'm just highlighting, it is offset feed structure without slots on the top layer. But after introducing, then you are getting this curve. After introducing that slots, L-shaped slots, then my lower cutoff frequency is somewhere else 3.1 gigahertz. So with this thing also, I just want to conclude that with the presence of these slots, L-shaped slot, my resonant frequency, or I should not say resonant because it's not resonant, lower cutoff I should say, minus 10 dB lower cutoff frequency is shifting from somewhere else 4.5 gigahertz to 3.1 gigahertz. So this is how we had followed several steps. Then we had come to this structure. So it may be the work of at least 3 to 4 months, because it is not possible to do this kind of design within maybe 10 days or maybe 1 month and all, because you have to perform many studies, understanding, then you just have to alter your structure. So this is done by my team and me. So this is about my ultra wideband structure. So at this point I'll just take some small pause, so that if someone is having any queries, then they can ask me. Then I'll just introduce another structure which is done by me and my team, which is directional terahertz antenna. So I just want to have any queries if someone is having, that would be more, good for me. Your inputs also important for me. Yeah.
Hello.
If anyone is having any queries, please let me know. One or two questions so that we can move forward.
Hello.
Yeah, yeah.
Sir, while designing Vivaldi in HFSS,
Your voice is little not clear, please.
sir, can you hear me? Am I
Yeah,
audible?
you're audible.
Sir, I am asking, while designing Vivaldi in HFSS,
Yeah.
what is the criteria that we can choose, like the flare angle or the equation? How can we define? Can you please tell us, sir? As my research area is antennas, I am asking this question.
Okay, I understand. While designing Vivaldi antennas, you want to design the structure with equation based or
Geometry based.
equation based, or another point? What is that?
Or which is the better method? I mean, how
See,
much is the flare angle?
sometimes what happens is that if you follow literature, then it is the credit of the author who has done it. But if you want to explore your own structure, then you just have to come up with the structure, then you just provide mathematical support. That is what we do, because many other times I don't follow literature structures, because it is the credit of that particular author. Then what will be the credit from our side, right?
Yes, sir. Yes, sir.
You got the point, right?
Yes, sir. Yes, sir. Thank you, sir.
Okay, okay. Then any one more question if someone is having? Last question. Okay, then I think we should proceed further. We are running short of time. Okay, then another thing, we do have some work which is done by a team in terahertz technology. I just say that the reference frequency is 300 gigahertz, 0.2 terahertz, because nowadays people are looking into terahertz because it's completely, some kind of advantages we to have, because it can pass through clothing, paper, cardboard, wood, plastic, ceramics, and then another important point, it is like high speed within line of sight communication, I should say. In fact, it is not standardized, but the things are going on, means research is going on in such direction, because now people say electron 6G or maybe 7G. Then in such case, maybe terahertz would be the better option. That's why people are looking in the 100 gigahertz to this range, 30 terahertz, so that the things will go smoother, at least in short distance, because as frequency increases, then the attenuation increases, right? It is attenuated by the air molecules or water molecule. By considering that, you have to limit your distance. So that is another important point. Now, one standard we have is IEEE 802.15.3D, which has just some reference range 252 to 325 gigahertz for some wireless communication networks. It is a standard proposed and then maybe existing. So by considering that, we had come up with some structure. Again, here, our motive is to come up with the structure directional property. Then that structure is this thing. And then you may be thinking that, sir, we had, or maybe you may be thinking that it's a mixture of some several structures. Yes, again, same thing. We do have some directional enhancing technique, which is your directors. Okay. Another thing, it looks bow tie. It is not exactly bow tie or maybe something. Someone may say that it's a bow tie. Yes, I do agree with that. But it is not a tapered one. It's a tapered one. I'll just see what is the credit of tapering, that is broadening your width and then shortening this width. And then here you to have a partial ground here, and then you have directors. Then you can see here, it is terahertz, so I cannot use normal materials, conducting materials like copper and all. Yeah, you can use copper and all, but still people prefer higher conducting materials like gold, then graphene, such kind of materials. And then again, yes, the substrate what we have used is a silicon dioxide, because it's a terahertz frequency. You cannot use FR4 or RT2, but still, yes, for simulation study and all, people do that. Researchers adapt that. Yeah. So this is what the structure. Again, yes, we have several steps to follow. Uh, Here again, there would be many learnings from our end, from my end also. The point is, yes, this is what you have S11, somewhere else from 240 terahertz, gigahertz, sorry, 240 terahertz to 325, which is as per the standard IEEE, that whatever the standard we had. And then you can see here, just by putting some directors over here, no directors and all, then you can see some kind of gain enhancement in this frequency range because of these directors. That is what I can show. But here I'll just show this is directional property. Yes, this is what I have simulated in the CST. It's not in HFSS. Earlier work was done in HFSS, and this is in CST. Okay, so I'm just getting good gain actually. Gain is around 10.4 dBi. That is what the good gain. And then you can see here, this is my structure, internal structure, and then this is again, you can see the end fire directivity I'm getting with director, without director, it's fine. Okay, so then here I just want to show this thing, that this is conventional bow tie. Now again, this work has like we have derived this work from the conventional structure, but ultimately the structure is little different from the existing work. Now this is what we have is a conventional bow tie, and then this is with full ground. The structure is with full ground. Now if you look at here, then yes, it will give you some S11, but the point is, my point what I want to discuss here is that directivity, its radiation pattern in the XZ plane. Basically, what I want is in the end fire direction. End fire direction in the sense, I just want my pattern to be in the YZ plane, not in the XZ plane. Now, if you look at here, it is perpendicular to the plane of your antenna. Okay, but I want my directionality along the plane of antenna existing. Okay, so now if you look at here, then the directivity is along XZ. Now by employing here partial ground, yes, you can see here this is with full ground. Figure A is with full ground, and then if you look at here partial ground, it is with partial ground. Now you can observe a clear cut difference. This is what the directivity towards my YZ plane, because now this is something and then another direction, but this is what from my end fire radiation. So this is what I'm expecting. I expected, and then I did, and then you can understand that, oh, by putting partial ground here, what is happening, it is acting like a reflector. Because whenever you consider a Agawad antenna, then you'll put a reflector back to this active element, then your back radiation is completely forwarded, so that you will get the end fire radiation. Here also, by looking into that structure, what I had is that I had one partial ground structure over here, and then I just tried whether it will work, because I know that in Agawad case that by putting the reflector it is working. Now I just had a mind something in my mind that what happens if I put partial ground in my structure. Then yes, it has worked well, but still you can see that it is not perfect directional property. Then what we have done is we have modified the structure to this one. Means we just had put bow tie arm on the top side, and then some bow tie arm on the top side. It is symmetric. What we do generally is simply in a one plane you put direct this bow tie, but what we had done is we had split it into left arm, right arm, then half portion is put over here, which is on the top plane, and then it is on the bottom plane. Now it is balancing, okay, because left side radiator, right side radiator, they are balancing each other. But whenever it comes to this structure, it's only one radiator. Because of this one radiator, you will not get complete directionality. Okay, and even though you put partial ground, you see here there is completely missing radiation pattern. So this is another I should say that another learning point for the community, for me as well. Whenever I put offset feed, in fact it is, you know, center feed, it is again center feed. Then whenever you put center feed, what exactly happen, your radiation cannot point towards end fire direction 100%. So again, if you look at the structure, yes, again you see here, this is creating offset feed, whether it is left arm or right arm, then absolutely it is offset feed mechanism. So that's the reason I got completely balanced radiation pattern towards end fire direction. But if you see here in this direction, the maximum is not achievable because of the center feed. So that's another point I just want to put up in front of you. This is yeah, yes, this is already works are published, and then not in underview, I think they're, yeah, they have published only. So but my point is that only I just want to tell these points to the community, so that will follow the same thing. So this is what my intention of putting some techniques related to directional property. and just let me confirm the timing from the team so that I'll see what I need to do. Dr. Virender's, like,
yes, sir.
how much time I have?
Am I audible, sir?
Yeah.
You can carry, sir, for 5 to 10 minutes, sir. Can carry.
Okay, yes. Thanks for this confirmation.
Okay, sir.
Yes, yeah. I'll just share again. This is what my study. Is the screen visible?
Yes, sir.
Visible, sir. Visible.
Oh, thanks. Okay, so this is another word. Yes, right. Thanks. Now, this is what cognitive radio, but this is what integrated multiport, planar, and narrowband system. I just say that these are the integrated structures on a single substrate. Now, I need not to say maybe cognitive radio community knows about it. You just sense it. If it is free, then utilize it. Okay, it's too long to discuss about this concept, cognitive radio. Yes, still it is little older concept. I don't say that it is new concept, but still you are people are publishing papers in this domain of cognitive radio, especially in case of antennas. So you propose reconfigurable antennas, ultra wideband, narrow band, in this 3.1 to 10.6 range only. Here, for the first time into, I should say that community, what we had this structures. So let me just expose that cognitive radio. Mainly the concept is cognitive radio in the sense, suppose like if you consider a classroom, then if someone wants to interact with the teacher, then all students cannot ask queries at a time, right? So that is the concept of cognitive radio. What the student will see, if someone is speaking or someone is asking the question to teacher, then remaining students will be keep quiet. I am understand assuming that students are good, otherwise they create nuisance. Yes, so one student see if someone is speaking, then we don't have to speak, and then once he finish another student, then the second student continues, then second finishes, then third student continues. Here also cognitive radio, what exactly happens is that the complete cognitive radio system checks what frequency is available. Okay, so it scans the radio environment. So there are some techniques to scan, use ultra wideband antenna and all, that's okay. But someone has to sense what is happening within this radio environment, whether the particular frequency is available or not. Because the point is 3.1 to 10.6 is unlicensed, anybody can use. I'm just assuming that there is no limitation on the power. Okay, if you have power, then you need not to sense it angle, but I'm just assuming that you don't have any limitation on power. All are having equal rights to you know speak. But what is happening, if I speak when someone is speaking, then it creates nuisance. I just don't want to create that nuisance. Then in such case, what I'll do is I'll just sense the radio environment, what is happening, whether someone is speaking or not speaking. Then I'll sense it. If someone is not speaking, then I'll speak it. That is what exactly applicable. And then yes, why I need to select 3.1 10.6, because it is unlicensed, anybody can use it. So I should be very careful that whenever you are sending some signal, then you should ensure that nobody is sending anything. So the moment you just have it, then you can use it. So I just quickly show that what is happened, what has available in the literature, and then what our team and myself come up with. So these are the fundamentals of cognitive radio technology, and then you can see some kind of with power limitation, without power limitation. Yes, I'll just go quickly. So this is literature. What ultra wideband antennas you have, mostly people come up with partial ground, because that is the easiest way. Then people come up with metamaterial, then fractal structure, then notches, like reconfigurable antennas. They put slits also to get some. They come up with dielectric resonator antennas also. And they too come up with frequency reconfigurable antennas, like they use varactor diodes, or maybe pin diodes to create some reconfigurability in the frequency, because many of the times you may not be happy with single frequency and you don't want to have it single. So what you do, you employ either vector diode or maybe pin diode, so that you will get this particular frequency reconfigurability. Now this is what reconfigurability structure, because it looks interesting for me, because there would be more what you want your feed line, this needs to be connected with one structure. Now when you rotate this one, so there would be four structures. This is one structure, and this is one structure, and this is another structure, and this is another structure. When you rotate it properly in a certain angle, then different structures align with the feed line. Now that creates your a different resonating frequency, either dual band or multi-band or whatever. So that was very interesting study by these researchers, maybe in this reference. I felt very interesting during that study. Yeah, so they use motors actually, because someone has to rotate that plane, right? The alignment needs to be with the feed line, so they use motors. Yeah, there would be losses and all remaining things, it's fine, but it was interesting. Yes, you then you have some reconfigurable structures they put. Yeah, and another point here is, for what I was talking is cognitive radio. Many of the times what happens is you have to sense it and you have to communicate. Okay, because when the student is listening the class, how he senses, he use his ears to see if someone is checking, and then he speaks with his mouth, right? Here we don't have that system, because for sensing he use ears, and then for speaking he use mouth. Here we use ultra wideband antennas for sensing, because the moment we say radio environment, everything is antenna. So yes, we have ultra wideband antennas for sensing, narrowband antennas for communication. I'll just go quickly because I think running short of time. So this is what I was talking about, this dual port antennas. So here you have two structures. One is on a single substrate. Okay, single substrate. Don't think that it is on a different substrate. No, this is your ultra wideband. Maybe this is narrowband antenna, and then this is another interesting study by this at this point. And then again, you see this is also interesting. You see here, this is on the top plane, and this structure whatever on the bottom plane. So that is another way of integrating ultra wideband and narrowband antenna structures on this single substrate. Now you can see here, whatever I have shown previously, that was a single port, but here they had come up with this is ultra wideband antenna, and then this is what reconfigurable narrowband antenna. So this is what existing in the literature. Means they use reconfigurability, maybe ultra wideband, narrowband. And from our side, what we had done is, means our team, in fact it is my thesis work. What I did is, this is my ultra wideband antenna, and then it is coming up with multiple narrowband antennas, because literature restricted so far, means till that point whatever I was studying, they have restricted their study to dual port, means one ultra wideband antenna and one narrowband antenna. But what I come to what the thing come to my mind was that I should use one ultra wideband antenna and multiple narrowband antennas, so that, see, this guy can communicate at a time, this guy, this guy, this guy. Like that, you can use multiple communication task at a time, because here you have only one narrowband antenna, though it is reconfigurable. At a time it supports only one frequency. But what comes to what was coming to my mind at the time was that, no, I don't want to restrict my communication only one time. I just have to make multiple times. So that with that idea, what I did is, like, I integrated multiple narrowband antennas onto the ultra wideband antenna. Yes, I just show highlight this work. So this is a simple ultra wideband antenna. We have top plane, bottom plane. Then you can see here, this is a 3-port structure, which was published in IJAP long back. Okay, so you can see here there are two narrowband antennas which are integrated left and right. Next, this is another interesting study, which was in IEEE transactions long back during PhD. This is my ultrawideband antenna, and this is what my 4 narrowband antennas. So all will have their own frequencies. This is what you can see, and you have same ground plane or different ground planes. Okay, and then this is what wireless communication system we had developed. Then if I go continuously, then it will take at least more half an hour. I don't think I have time. Then the
Sir,
beauty, yes.
we are sorry, sir, because nobody want to stop this type of practical lecture. And in spite of that, so many of our participants belongs to antenna field,
Yes,
so
yes,
they
I
will
do
be,
understand.
they will not let me go. But sir, we have a next speaker with you next
Yes,
section,
yes,
sir.
I do understand, sir. That's
So
why
you
I'm
have
just
to. And
asking.
sir, one my question which is coming in my mind automatically from past half an hour, how to deal with the variation from software to software, like we are going from CST to HFSS or HFSS to CST. How to deal with this variation? As I have seen one of your slide was showing significant change in the gain, sir.
Sir, what we do is, that's why what we do, we'll just verify the same thing with the fabrication. Okay, because nobody
Okay, sir.
says that whatever you got result in HFSS or CST is correct. So we'll just, it's a tool to just let us see what exactly we are getting, and then you verify from the fabrication. So it's all, you know, mutual. Even it is not, you cannot say that in the fabrication whatever the result you are getting, it's the final, nobody can say. But what
Yeah,
is the
sure, sir,
point?
sure.
But what the technique you have used, it will be correct whether you use CST or HFSS. Then it gives you proper, like, directionality means it gives you directionality, maybe 10, 10.2, 11, that's okay. But ultimately we should post focus on the technique actually, from my understanding, what I feel.
Okay, sir. Thank you very much. HOD, sir.
Yeah, thank you very much, sir.
It's my
Anvesh ji. It's
pleasure, sir.
actually I'm also basically done my research work under the same topic,
Great, sir.
reconfigurability only.
Yes, sir. Yes, sir.
Reconfigurability only. So on tried frequency, pattern, hybrid, tried, and a lot of work has been done.
Great, sir.
Published around 8 journals also, reputed journals also.
Good,
So
good,
it's
good. Good to
very
hear that.
nice. Whatever you explained, it's very good, sir. Nice, and we are very happy to be associated with you today.
I do expect, sir.
Thank you very much. We'll be in touch with you for sure, sir. Thank you. Thank you very much.
Thank you,
Any
sir.
queries from sir? Come again.
Thanks for the invitation to the Virender Singh, and then to you also, especially. I should mention. I hope that we'll work together in later on in some other
Sure,
works
sir.
and all.
Sure. We would love to collaborate with you.
Thank you very much. It's my pleasure. It's my pleasure.
Yes, sir. Thank
So
you very much.
do we
And,
take 1 or 2 questions, or should we wind up?
yeah. Any questions from anybody, participants?
Sir, this is Santosh from Andhra University.
Please tell me, Santosh ji.
Sir, good afternoon, sir.
Yes, yes.
Sir, I have a small query regarding bandwidth, sir.
Yeah.
So, what is the major difference between narrow bandwidth, wide bandwidth, and ultra wideband? And nowadays we are seeing super widebands.
See, super wideband. See, as of now in the literature, if you look at, then 10%, 20%, more than 20%. So narrow band, wideband, ultra wideband. Super wideband means, like, so far in the literature, it is not like someone has mentioned it. Maybe everybody are having their own perception. So someone say that if it is, like, say 2 gigahertz, 5 gigahertz, then they may say super wideband, right? Okay. Something like that, but there is no definition of super wideband in the literature, so they had restricted it to ultra wideband because of 20%. And then it is now everyone perception. You cannot say that this is long or this is something long. It is depending upon their perception. Santoshi, am I clear? Yeah, I think
Santosh.
Santosh ji. Okay, maybe any other query?
Sorry, sir. Am I audible, sir?
Yes,
Yeah,
yes.
audible.
Sir. Sorry, sir. And how can we say? I mean, for what percentage we can say it is whether it is a narrowband or wideband or a ultra
Below
wideband?
10%, below 10% of fractional, you can say narrow. 10
Okay,
to
sir.
20% wideband. More
Okay.
than 20 ultra wideband.
Ultra wideband, sir. Okay, sir. Thank you, sir.
Yes.
That's my major query. Thank you very
Okay.
much.
Okay, Santosh ji.
Any queries from anybody?
Okay, sir. We should close this session.
One band pass filter bandwidth can take it.
Band pass. Yeah. Yes. For filter, minus 3 dB can be taken out. With respect to 0 dB, if you say that maximum is 0 dB, then minus 3 dB range is considered to be bandwidth. Yes, correct. And S11 obviously minus 10 dB would the your limit.
And thank you very much, sir. Once again, I'll thank from the Department of ECE,
Thank you, sir.
NSRIT,
Thanks.
Visakhapatnam.
Yes.
So
Yes,
until
sir. Yes,
we'll
sir.
be in touch with you, sir. Thank you, sir.
Sure, sir.
So,
I hope, sir.
I request the participants feedback link will be shared in the WhatsApp chat
So
box.
please let me know after the feedback also, because I have to mold myself according to the inputs.
Sure. Definitely, I'll share it with you.
Because if we want to learn every time, so we want that thing.
Definitely, sir. Sure.
Thank you, sir. Thanks for the invitation.
Thank you
And
very
then
much.
thank you, Virender Singh, for the coordination.
Thank you, sir. Thank you very much.
Okay, sir. Then see you soon, guys. See you soon.
Thank you.
Actually, sir,
Virendra.
Dr. Sripad Raja, sir, is ready, sir. Dr.
Yes,
Sripad Raja, sir.
hi Virender.
Hello, sir.
Can you hear
Welcome,
me?
sir. Welcome.
Yeah.
Sir,
Yeah,
welcome,
thank you.
Dr. Sripad Raja, sir.
Yeah, thank you very much
Sir, welcome, sir.
for inviting me for this session. Hope today we'll be able to communicate something what we have, what is intended, that simulation of some MEMS devices. Okay, so hope it will be useful. So we'll see that. Yeah.
Yes, sir.
Let us give us a minute for a profile reading. Let the participants know. Now I request Shivaji to read the brief profile of Dr. Sripad Raja, sir.
Yes, sir. Thank you, sir. Am I audible, sir?
Yes, audible.
HOD, sir. Dr. Sriprasad, sir. Welcome, sir. Welcome to this FDP. Dr. Sriprasad, sir, completed his PhD. He done his master's from Bangalore University. After completing his PhD, to work as application solutions from the year 2008. Then he moved on to Sridat Technologies, which is a sub-branch of intelligence software, where
I think some issues there with audio.
Sir, link is not work. I think something has happened, sir. You can continue, sir. Dr.
Yes.
Sripad Raja, sir.
Wait.
Continue.
I'll read, sir. No issue. I'll. So Dr. Sripad Raja completed his masters in electronics from Bangalore University and PhD from NIT Suratkal. He started his career in MEMS as a project assistant in IISc. So later, sir has joined Big Tech as an applications engineer. He was a senior application engineer and subsequently a product manager after the IntelliSense software team set up a new company, Sridat Technologies Private Limited. So then he has conducted many training programs and has given many invited talks across India. He's associated with IntelSense and its associated business for more than 12 plus years. He's now operating in the capacity as a managing partner at IntelSense Software India. So, uh, he previously worked as a in different positions: product manager, senior application engineer, product assistant in different capacities. So he's an experienced product manager with demonstrated history of working in MEMS industry, skilled in computer-aided CAD also, simulation, training, and strong product management professional with a PhD focused in microfluidics from NIT Karnataka. So this is a brief intro about our today's speaker, Dr. Sripad Raja sir. So I welcome you once again, sir, for this session. Please continue, sir.
Yeah, sorry, I was in mute. Thank you, Dr. Shiv Prasad. Thanks for the introduction. Hello, everyone. This is Sripad here. Professor has already given me my background. So today we'll be discussing about how the MEMS simulation and the need of MEMS simulation. So am I audible? Is the voice very clear?
Yes, sir, audible, sir.
Yes, sir, very much.
Okay, great. So I am sharing my screen now.
Yes, sir.
Okay. Yeah, can you see my screen now?
Yes, sir. Starting.
Right. Okay, so I'll just minimize this. Okay, so I'm put it onto the slideshow mode. Right?
It's
okay.
Fine, sir.
Great. Okay, thanks. Fine. So now I think for a while, I think I can switch off my camera, right? Yes. Okay, fine. Okay, so now the outline of my talk is about what is a sensor and why MEMS sensors, and what are the advantages and disadvantages that are there, and some of the MEMS design and development, a complete cycle. We'll see that, and how the structural design and the process optimization will be done. And then some research opportunities is what we'll see. How many of you are aware of what MEMS is? Can I know some background of it? Hope at least the name you might have heard about it. Yeah, so okay, so I also see that there is one more lecture about MEMS devices tomorrow from a person from ACL Chandigarh. Okay, so he'll be talking more about the specifics of the device. So here my presentation is restricted to how the simulations can help in building MEMS devices. So to start with, the background of MEMS is it's an integration of mechanical elements, sensors, actuators with the electronic circuit on a common platform, and with electronics are fabricated using the same IC technology. Okay, but only difference that is there is a process called as micromachining. I mean, these are just words that you need to remember now. Let's not get into the specifics of it. Okay, so here with the difference between the IC technology fabrication process and the MEMS fabrication process is that the MEMS fabrication process delivers a moving structure, a movable structure, mechanically movable. But whereas the IC technology, there are no moving parts in IC when we develop IC. So that's where the difference between the MEMS process and the IC fabrication process. Both use the same CMOS method of CMOS technology. So why it is MEMS? It is small in size, it's a low power consumption, lightweight, low cost, portability, reproducible manufacturing cost, and excellent control of material purity. It has precise control of dimensions, integration of multiple functions, and integration with electronics. Okay, So there are few successful MEMS devices which are already there in the market. The three major sensors, the MEMS sensors that have already captured the market are the accelerometers, the gyroscopes, and the microphone. Okay, so these are the three major MEMS devices which are there in the market now. So accelerometer and gyro are already there in the consumer electronics, mobile phones. Okay, microphone are there in the laptops now. So it's already reached the consumer market. So when we look at the application part of it, so we will have varieties of domains like the aerospace and biomedical, automotive. So if we look at the inertial sensors and the pressure sensors, so it is required by aerospace, biomedical, and automotive. Flow sensors, again biomedical, automotive, and aerospace, chemical, industrial, safety, food technology, healthcare, pharmaceutical, and RF MEMS, aerospace, and communication systems. So wherever there are communication systems, so you require RF MEMS sensors or the actuators. Okay. So here the idea is that it's a sensor. So let's understand what's a sensor. Sensor is a parameter which measures a physical parameter and then converts that to a equivalent electronic signal. Okay, based on the quantitative measurements that are based on the qualitative measurements that are done, it produces a quantitative results. Okay, so that we can try to understand the physical parameter, what are the one which we are trying to measure. Okay, so here we have the mechanical and thermal and electrical optimizations that we do. So all these three things are involved in MEMS devices. So when we look at the design methodology, the design requirements, the basic design and optimization is what we do. So we collect the design requirement based on what is required, and then we do the basic design and further optimizations we do. So how do we start? In this thing, when we start through a computer aided design, okay, a 3D CAD model is designed, and further a lot of simulation goes through it. So how do we do it? The simulation. What are simulations? A simulation is a parameter where we try to make a physical environment across the sensor and try to understand how the sensor behaves. So earlier lecture you were talking of HFSS and you were talking of CS, I think Studio, I think one more EM tool. Okay, so the simulation. So similarly, there are simulation softwares for MEMS devices. So what we do is we do the simulation of, we do a multiphysics simulation basically, but a thermo-electromechanical response. Okay, thermal, electrical, and mechanical response is what we calculate, and then based on that we do the ROM, reduced ordered model simulation, and further we do the SME, system model extraction, and further a system level integration. This is what the whole process goes through. Okay, and further once it is done, we create a layout. Okay, and then we define the process. When we define the CMOS process, that is the process optimization is done, and the fabrication process and testing happens. Okay, so this is the design methodology that are there. So the challenges, there are a few challenges here. So the challenges are like the FEM, first challenge that we see is building a 3D CAD model and trying to optimize. So it's a multi-physics simulation where the physics can be thermal, mechanical, electrical. Okay, so based on that, we try to optimize the design for the requirement. So the next challenge that we encounter in the development of MEMS device is the readout integrated circuits. The sensors that are developed is all fine, but someone has to read the signals and then make it into a readable format. Okay, so we'll have to do that as well. So, and further, once it is all done, we will have to do the process optimization, a method to fabricate or manufacture the device. So we will have to do that. Okay, so there are challenges in three different steps, three levels. So first is the FEM, that's the multi-physics simulation. Second is integration with electronic circuits, and third is the process optimization. So let's look at what are the challenges that we will see in FEM design. Okay, a 3D CAD model we create, and then we perform a multi-physics simulation. I use the word FEM because we use element method, finite element method, or the mesh model, what we call it as, and then we define the parameters of the simulation, and then the simulation is carried out. Again, the response will be different. So it is not meeting our requirement. We again create a model, and then we again simulate, and then with various other parameters. So for such a cycle or repetitive procedures, there is some solution available. A solution is that what you should do is you should parameterize the structural. Say for instance, you are trying to design some cantilever beam or any accelerometer or any RF device, phase shifters. Sorry, I think the RF switches, the vectors. So whatever you are trying to do it, so tune it, tell the software that these are all some of the dimensions that I want to do, and you can define it to the software so that it saves a lot of time for you to redesign the whole process, or else it has to be manually redo it. I mean, you have to redo the whole design again and again to optimize. That's very difficult. So tell the software, these are all the set of dimensions I want to simulate. Okay, that's one. The second is, these are all the range of variables as an input is what I want to feed to the software. And further, once both things are done and once you are ready with the design, then you can extract the system model and then perform the reduced ordered model simulation. Okay, that is one. And second is challenges in element-based modeling. So here we have two different types of approaches for the design. One is the bottom-up approach using the fabrication process flow, the CMOS fabrication, wafer defining, deposition, lithography, etching, bonding. So 4 major steps of fabrication process. So that is the bottom-up approach. So what we also have is something called as a top-down approach. So top-down approach, we have these elements, just like PSpice netlist. There are few MEMS elements. You can drag and drop them and then connect it like a circuit and create the MEMS device. So for that, the system level simulation, and again, the parameters are defined. You have to modify the design. So for that, again, the solution is you should parameterize the structural and you should parameterize the input variables. Okay. And we see the third level of challenge. One is the challenges in the process. So for that, what you do is you have to create a layout and then do the process recipe and process integration. Okay, let me give you an example. So I'm not sure how many of you are aware of the microfabrication technique, but microfabrication is the process that we also define. We call it as a recipe. The recipe is a term which is used only for cooking in layman's language. Recipe is a word which is used in kitchen. Okay, it's to prepare a dish. So when you prepare a dish, so you are in Vizag, so there are 100 number of hotels. You get Andhra varieties like you have the upma pesaritu, punugulu, whatever you want to have it. Each hotel has a different taste. Why is that happen? The procedure remains the same. Okay, and the ingredients are the same, but during the process there are few changes that will happen. Okay, so that's why. So whenever we try to fabricate some device or manufacture some device which is also a recipe, it has to be standardized. So for that, to meet our requirement, we should do the design based on the design rules of the foundry. Okay, that is more important. So whatever the simulation that we do, if we are happy with the simulation and we want to complete our work only with the simulation, you can do any number of simulation with any values or any dimensions or any requirement, no problem. But you are thinking beyond, if you are thinking beyond the simulation and you want to try to fabricate, then all these CMOS-based design has to pass through some design rule check, because there is someone else who will fabricate the MEMS device, the sensors. Okay, and it has to be process verification oriented. So these are some of the challenges, and these are the solutions that you need to adopt. Okay, so we'll see some of the multiphysics simulation examples. Like we have a CBAC effect simulation where we perform a non-linear based model simulation, which is the micromirror example. And then we have a cantilever beam and a resonator and a packaging simulation as well. So we have a resonator which is used in your RF device, a mechanical resonator, or we also call it as a bandpass filter or a filter. So we have mechanical where it resonates at a maximum amplitude for a particular value of frequency. Okay, and then we have some benefits. So what the benefit that we get in simulating is that the entry point is via the 2D and a 3D model. So you don't have to really worry about the the difficulty in designing. And then we have something called as preprocessor, where we do the simulation settings. And with parametric simulation, you save a lot of time. And with post-processing techniques, you get the results in visual format. Okay, and then in element-based model, you have elements like this is a bandpass filter. Okay, so it resonates maximum at a particular frequency, which is defined already. Okay, so these are the elements that we can you can simulate, and this takes a quick simulation. Okay, it's just a quick simulation run through. If FEM simulation takes about a day or two, and these element-based model simulations take a minute. That's all. Okay, so these are basically a Lagrangian models, a lump model kind of simulations, and the results are all in 2D and 3D. And these can be exported to the FEM and layout creation. You don't have to redo the whole thing again. Okay, and here when we talk of microfabrication, so the 4 major steps of microfabrication technique is the deposition, is the lithography, etching, and bonding. Okay, so these are the 3 major steps for the microfabrication technique. Okay, so here there are a few research opportunities in simulations. Okay, so what are all the things that you can? So I hope most of you are from academic background and quite interested in to do a possible research in this MEMS technology. Okay, so you can parameterize the structural. So when you parameterize structural, the structural model, then something like this. I'll take an example of an accelerometer. Okay, accelerometer is designed to resonate at a particular frequency. Okay, and you are trying to optimize them. And when you try to do that, you have to recreate the whole design. So the solution that I offered is you can parameterize the structural. So when you parameterize the structural, it simulates for a lot of dimensions, and then it produces the result. So something like this. Change in the first graph, what you see is the change in the natural frequency for parameterizing the beam length. So as the beam length is increased, so the frequency of resonance is also coming down. So what you see is the green line is the mode 1 and the mode 2. Okay, and similarly what you see on the second graph is the change in the displacement versus the parametric load. Okay, so it changes. So similarly you can do it for comb structures where it is used in accelerometers and gyroscopes, piezoelectric beams, and piezoresistive. So all these type of sensors, you can parameterize the structural. So what is the benefit that you get by parameterizing the structural is that you have complete data of how your system behaves. You can derive equations out of that. And if you plot a graph of how the linear, how the length of the structural is varying for the input given, you plot the data, and then you can extract a polynomial and a quadratic equation and try to understand how the curve fits in. Okay, so that will give you a linear and non-linear behavior of all these MEMS devices. Okay, and once this is all done, we capture the harmonics and we capture the energy associated with each modes of vibration, and then we convert this into a HDL model file and then put it into a electronics. Okay, so this black box, what you see is that this is the MEMS device. Okay, we put this onto the black box and then integrate electronic circuits to interface for the, I mean, this is basically interfacing electronic circuits. Okay, so here what you see, the black box. And remember, for any of these micro sensors, you cannot have electronic circuits being simulated along with the sensor. Okay, this is the only way to do it. Make the reduced order, extract the reduced order model file, put this into the black box, and then do the other connections here. So integrate your signal conditioning system to your MEMS device through reduced order model simulations only. So what is the outcome based on this? The reliable result, and it is benchmarkable. So because you are trying to benchmark with two different models, one is the FEM model and one is the Lagrangian model. And you can compare the results of FEM and Lagrangian model. A comprehensive study of the design by parameterizing the structural, you have complete understanding of how the structure, how your sensor behaves for various dimensions, and with behavioral study for range of load. So by parameterizing the input variables and also the structural, you have more clarity in operating range. So when you have complete information about your device or the sensor, naturally targeting the sensor to tune it to a specific application becomes very easy. Okay, so you should think of parameterizing and understanding the structural behavior of the device. Okay, and further, the element-based models. So here you get digital, electrical, general, and MEMS and thermal elements. And further, you can parameterize the structural as well. So with FEM also, you can parameterize the structural, and with element-based models also, you can parameterize the structural. So with parameterizing the input variables, the material properties and ambient conditions, your Lagrangian model can be very quick and with reliable results. Okay. So some of the MEMS devices that you can simulate using the Lagrangian model or the lumped model using the elements are something like this. So using the same elements, you have a fixed cantilever beam with a serpentine spring connected. And we have a serpentine spring anchor connected to a plate. Okay. A beam and a plate is connected. So this cantilever beam, and using the plates and beams, you can create an accelerometer, and with the same plate, same elements, you can get a gyroscope as well. Okay, so there are lots of benefits that you get by using the element-based model simulations. So parameterizing using element-based model. So how a parametric simulation can help you. So this is an example of an accelerometer design. The thickness is varied from 10 micrometer to 20 micrometer. The amplitude of vibration is changing. So the formula for a resonance is omega is equal to root K by M. So here K and M, so the thickness is being increased. Okay, so here by parameterizing this structural, so you can see that there is a change in K, that is the spring constant, and also on the mass. Okay, so that is contributing to the resonant frequency amplitude. So another parameter that we can vary is the ambient condition, where we have a pressure of ambience. So what is the standard atmospheric pressure is 101.325 kilopascal, right? So when different ambient conditions are set, the device performs differently. So you can see the amplitude of vibration changes with change in pressure. Okay, so that can also be plotted. So these are the factors that contribute to the damping of the system. Okay, so usually we consider zeta as some arbitrary value and then we perform a lot of simulation. But what is causing the damping factor? So it's the environment around. Okay, so it's the gas that is around, that is the air that is around. So you have to capture based on the mean free path of the gas. You have to capture based on the temperature of the gas, the pressure, the viscosity of the gas, and the mean free path of those molecules. So these are all the factors that contribute to the damping factor of the device. So these are taken care in by simulations. The outcome, what you get is the FEM based model, that's the simulation, and we have the parametric simulation, the dimensional, load, and material properties, and the static, frequency, and dynamic simulation. Static is basically one input, one output response. Frequency is the resonance curve, and dynamic is the response of the device with respect to time for the given load. Okay, and results are generally ideal unless otherwise, because here FEM simulations are considered ideal unless you define any specific dashpot or any spring or any damping factors. So if you don't define any damping factors, the results are all generally ideal. With the element-based models, what you get is simulation is possible with MEMS sensor in integration with electronic circuits. You can also parameterize the structural, the dimensional, load, material properties, and static, frequency, dynamic simulations are possible. And then results are based on ambient conditions. Okay, so the ambient conditions, the pressure and temperature, viscosity of the gas around the device. Okay, so at this stage, I'd like to take a pause and then further move on to microfabrication process. Okay, so do I have any questions until now?
Yes,
No
sir. We will take
Questions from the
at the end, sir.
Yeah, okay. So if there are any questions on the chat box, please read it for me. I cannot see the chat box.
Sure, sir. Sure.
Yeah, okay. Are there any questions until now?
Good afternoon, sir.
Yes.
Myself, Rama Gauri from GVP College of Engineering, sir.
Okay.
My area of interest is digital VLSI. After
Okay.
attending your lecture, now I'm in a position to understand the difference between VLSI and MEMS exactly, sir. But
Okay.
here my doubt is for VLSI circuits simulation, generally we are using the CAD tools like Xilinx, Mentor Graphics, Cadence, all these. For
Correct.
this simulation process of this MEMS, which tool we are using, sir?
I am using IntelliSuite software for all the simulations.
Okay, sir.
Yeah.
But if we want to do work on these MEMS, do we have the idea regarding this mechanical system, sir? Is it required?
Not very much. See, as you go higher and higher in research, things will become interdisciplinary. Okay. So
sir.
there is nothing like we have to master everything. So have a friend who can contribute mechanically and do the teamwork. That's all. That becomes easy. Or else trying to learn the every process of the MEMS. I think one person will soon die understanding the whole process, because fabrication is a different thing.
Okay.
Mechanical optimization, electrical optimization, power optimizations, packaging, many things are there. Okay.
So it is
So
a
it's a team effort.
multidisciplinary research work.
Exactly. Exactly.
Okay, sir. Thank you,
Okay.
sir.
Yeah. Okay. Fine. Fine. Yeah. Any more questions, or should I continue? Fine. Okay. Let me continue. I assume that there are no more questions until now. Okay. So let me take you to how these things are being fabricated. So fabrication meaning preparing or manufacturing something. Okay. A clean room simulations. Why a clean room simulations are required? Okay. Because the MEMS fabrication is a costly business. If you ask me, are there any MEMS development company in India? No one is there. Okay. But if you ask me how many companies are contributing to MEMS development, all the companies that I will name have their presence in India. Okay. Texas Instruments, Bosch, ST Microelectronics, Lucent Technologies, Inventions, um, 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 Analog Devices, all the companies are having presence in India, but none of them are working on MEMS devices in India because MEMS is a costly business. Okay, so they have all set up outside India. So that's where the simulation will help a lot. So fabricating a MEMS devices is a costly business because it requires a huge clean room setup. Okay, class 10,000, class 1,000, class 100. So as we go lesser the number, the expensive will be the process. Okay, and you may be aware, or you might have seen why people use like dresses like the gowns. So what is used in the operation theater to enter into a micro fabrication area, because these are all the devices which are in the micrometers. Even a small dust particle can affect the device. So that's why it has to be extremely clean. Okay, so extra cautious is taken care to fabricate these devices. But as a beginner, how do I try to fabricate the device? As a beginner, how did we learn programming? By understanding if it's C programming. All of us, 90% of us, learned C programming by writing the code hello world. Okay, that's how we started. And if it's a ALP, assembly language programming, then it is 8085, 8086 microcontrollers. That's how we did. Okay, so how did we do further? And then digital VLSI, as madam mentioned, the adder, subtractor, and registers, okay, counters. So that's how we understood with the standard process. So here also there are few standard processes that are there called as the MEMS process, multi-user MEMS process. Okay, so there is a lab called Sandia Labs, which has defined the standard processes for people who are trying to do fabrication at lesser cost. So there are few standard methods called as the polypumps, where there is a polymer layer into it. SOI wafers, using SOI, silicon on insulating wafers, there are few templates that are available. If it's a piezoelectric material, there are piezo mumps also. And Scream and Summit are the other two. So here we have a standard process which is defined. So when there is a standard process that are defined, then the fabrication becomes cheaper. Okay, how do we get op-amps and all the other ICs at 5 rupee, 10 rupee, 15 rupee thing? Because the cost involved in fabricating 1 million devices or 10 million devices is marginally different. If it is 1 crore, maybe 1 crore, 1 lakh will be another 1 million devices will come out. So as the production size increases with lesser cost, naturally the product price will also come down. Okay, so IC technology is well established already. Okay, when these MEMS sensor thing also, when it is at the production level, then the price will also come down. Okay, and typically it is a custom-made process flow. The MEMS processes are all custom-made process flow, and it has extensive material database, and then you can convert this into a Excel or a PowerPoint for you to communicate to any other process engineer where someone is fabricating it. So this is a custom process. So what you are seeing is a nano hole array example where it is a example of an optical waveguide. Okay, so optical waveguides are being used at terahertz frequencies. Okay, for when just like filters. Okay, when we go to terahertz, it becomes more optical. So building a tuner or filter there becomes difficult. So this is one such nanohole array, or the 1D and 2D glasses that we have. So the 1D coating and a 2D glasses that we have is basically an optical waveguide. Okay, so we define the custom process for it, and then we'll have to, how do we manufacture? In the process of manufacturing, let me not get into the details of each process. So we are trying to give a shape to a for a device. So earlier, what I understand from Dr. Virender's mention is that most of you have this RF background. So let me take the example of how do you create your patch antenna. Okay, you have a copper coated PCB. I assume you call it as PCB or a board, I don't know. And you create a mask, stick onto that and put some chemical and then put it in the jig. And then, so those areas which are interacting will be removed with the copper. Okay, so those areas which are protected by the mask, that will be remain. So that will remain. So that's what your antenna fabrication is done. Okay, so similarly here, the microfabrication is that we create a mask and then run through a chemical called as KOH, potassium hydroxide, and create various profiles. But in silicon, when we look at the orientation, it has different orientation. It is 100 is there, 110 is there, 111 is there. So which one has to fit in? You should, we should know. So we can try to simulate in all the three types of wafers and see the outcome. Based on what is the outcome, we will decide what is the wafer that is required, the wafer orientation that is required. Okay, so similarly, we have something called as the TMAH. People call it as TMA, and the abbreviation, the abbreviation is tetramethyl ammonium hydroxide. Okay, it is usually used for IC fabrication because the KOH will typically leave some residuals in these MEMS devices. So when it is, in IC technology. So these chargeable charged ions, when it has become residual, it may generate a ESD, electrostatic discharge. So that's why for fabrications which are below 10 micrometer, people start using tetramethyl ammonium hydroxide because it does not relieve, it does not leave the charged ions as a residual. Okay. And if we look at the mask layout, I'm using the same mask. There are different types of etching techniques. Etching basically meaning is providing a shape based on the requirement. So there are different types of etching. One is the isotopic etching, and another is and then in the isotropic thing, it is uniform etching. Okay, so and based on the shape, we do the etching thing. So the plasma, it's a straight cut. So generally, accelerometers and gyroscopes are fabricated or etched using plasma etching. Okay, so there are different types of chemicals. So why simulation is more important? Because the profile that we will encounter after etching will tell us how the device behaves. So with KOH alone, something like potassium hydroxide alone, a square mask which is kept created a shape something like this. But the same square mask changed its resulted the shape like square with angled side wall when IPA, isopropylene alcohol with some percentage was added. With TMAH, the profile looks almost similar to KOH, but when TMAH is added with Triton, which is a surfactant, then you encounter this profile. Okay, So another benefit of simulation is that, so usually any simulation microfabrication technique uses a mask. What should be the shape of the mask? But general thinking is that whenever I keep the mask and then try to do the etching, the size of the mask, the dimensions of the mask will be the same of the I'll put it this way. The outcome profile of the device will have the same dimensions of the mask. But that's not true. There are some problems, something like the overcut and undercut problems. Okay, so for that you need to do the mask optimizations. So here you should also try to simulate various shapes of a mask for creating various shapes. Okay, so creating an octagon structure in 100 wafer is different from creating an octagon structure in 111 wafer. Okay, so where you can see that we are trying to create an octagon shape. And here I'll pause this at this stage. Okay, here when I pause this at this stage, you can see that the evolution of the etching is happening. Okay, but when it reaches this stage, it has created 8 shapes. But when we try to etch further, it becomes hexagon. So the etching time, how long you need to etch, so that also matters. So it has to be accommodated in the simulation. Okay, so when we try to simulate all of these factors, then it becomes easy for someone to design and fabricate MEMS devices. So let me not put you with other etching techniques with quartz and sapphire. Okay, so let me just get on to some advancements that we see here is wafer level simulation, because usually what people simulate is one die. Okay, one die, but when it is fabricated, it looks like this. I mean, the fabrication happens like this, batch fabrication. Okay, but when it is really fabricated at a wafer level, there are a few other changes that will happen. So those things can also be monitored. A grayscale lithography or a 3D mask, okay, can also be defined. So here, this is a small video how a 3D mask or the grayscale lithography is being performed. Yeah, so this is the mask, grayscale lithography, and the outcome is based on the type of mask that we use. And with the different other materials, sapphire, wet etching of sapphire is a different ballgame. And anisotropic etch, the spray etching for metals is what we can also do. Okay, and something like this, like you can do a lot of parametric simulation for array-based devices. So when you have arrays, something like the micromirrors, accelerometer pressure sensors, then you have to do a lot of simulation because they work together. So usually micromirrors are the examples where they are not single devices. They are working together as a team. Okay, so we have array of devices. So you should do the parametric simulation of array of devices. Okay, so creating such an environment and trying to optimize the device using numerical methods is what simulation does. Okay, so you should also take care of defining the material properties based on temperature. Okay, because some parameters do change with temperature. Okay, yeah, so various other devices. Okay, and further is the MEMS plus IC. What you see is MEMS plus IC. So the gyroscope module, the MEMS gyroscope module, is integrated with 180 nanometer technology, the testing IC. Okay, so you can also do this simulation. This has a lot of potential. So because sensor is one part, but understanding the format in which the signals are passed through is what it takes. It takes a lot of difficulty. Okay, so integrating this with IC is a challenging job. So if you are a researcher and good at VLSI and trying to do a lot of microelectronic circuits, then find a problem where you can read a MEMS signal or any sensor signal and convert it into a readable format. That adds a lot of value. Okay, so overall, today's summary of my talk is that we talked about some introduction about what design is all about, and then we have the MEMS design at the top-down and bottom-up approach, and research opportunities in MEMS device by parameterizing structural and the physical behavior and the parameters, and then with finite element system model and extractions, how it can benefit the research, and then verification by benchmarking by comparing the results of FEM and system model extraction. Okay, and then the element-based modeling techniques and the process deviation studies, because all these processes or the microfabrication has to be simulated to understand how the device will respond when it gets fabricated. Okay, so those things can also be simulated well. So at this stage, I'd like to take my second pause to allow you to speak up on various questions that you have. So I'm at the last slide of my presentation.
Thank you, sir. Very, very rich content, sir. I belongs to MEMS field, and I can smell it that this type of visuals are not so common that you will go and you will take this visual. It's extensive work is being carried out, and you are just giving us the cream of that. So I like it, sir. And my question is, sir, as you mentioned, and we also know, sir, that no such dedicated professional foundries there in India. How we can approach those polymums, and then how we can approach that? Is it a schedule?
So
and how?
That's a good question. Actually, there is one company which has been incubated in Bangalore in a sense. Incidentally, there is one more forum called as the ISSS. Okay. So in ISSS, Institute of Smart Structures and System facilitates all these people working in MEMS by connecting and networking. So through ISSS, I'm the national coordinator for the community chip activity. So in case if you are fabricating a MEMS device, something like a micromirror or a pressure sensor or a cantilever beam accelerometer or a gyroscope, which is silicon based, then there is a call already where by end of this month, if you can register and submit your design, so it can be taken under the SOI MEMS process.
So and sir, how cost is getting to vary point to point? Is it the mask space? How much design space we are getting into that?
Okay.
Or depends on the complexity of the process?
No. SOI MEMS process is a very standard process. Okay. So what they have is that you are given a 9mm by 9mm area, and then they try to fit. They try to fit your design into that. So it's a community chip activity. Already 36 institutions have already registered. And in case if you
sorry, sir.
Want to do it,
9 cross 9 area, including the alignment mask.
No, including the alignment mask, it is 11mm by 11mm.
Okay.
Your inner space is 9mm by 9mm. And already 36 institutions have already registered. By first week of November, they will be submitting their design. So before end of this month, if you can register, maybe I can send you the link. Okay, so you can do it. The fabrication cost is 35,000 plus GST.
Okay, sir. Fine, sir. Fine.
Yeah.
Any query from the participant? Welcome. Otherwise, HOD, sir. Dr. Shiv Prasad, sir.
Any, sir, thank you, sir, Dr. Sriprasad.
Thank you. Yeah.
Sir,
Thank
it's
you,
a wonderful presentation, and around 3 to 4 members are working on MEMS from my department actually. So
Oh,
we are
great.
really
Okay.
looking for the fabrication actually, like MEMS switches only specifically.
Okay.
So,
Okay. Sure. Maybe if it is a switches, then if it, I hope it's not a metal, no? It's a silicon.
switches
or,
only.
Switches. Then it's a metal contact, right?
Yes, sir.
Okay. Fine. Okay. Okay. No problem.
Well,
Anyways,
they have some queries, sir. They have some queries, and they'll personally contact you, sir.
No problem. No problem. I can help because I started my MEMS career through RF MEMS only.
Oh, fine.
So, yeah. So I
nice,
can
sir.
understand how difficult is metal
I knew, sir.
Yeah.
A wonderful session, sir. Presentation actually. But what Virender said, you only presented cream of the complete thing.
Yeah, that's right. I did not get into any specific ones, just overview. Yes.
Enough, sir, and thank you very much for your time with us, sir.
Yeah.
So definitely, hopefully, the people will get something out of it, and they'll be go further in their research with the help of this one, sir. So once again, I thank from Electronics and Communication Engineering Department, NSRIT, Visakhapatnam.
Okay. Thank you.
Thank you, sir.
Thank you, Dr. Shiv Prasad. Thanks, Virender, for
thank you, sir.
introducing
Thank
me
you
to
very much,
your
sir.
institution. Yeah.
It was very, very nice. Thank you, sir.
Yeah.
Sir, sir, camera switch on, sir.
Okay. Sorry.
All the
I think I should
to switch on. Sir,
is it? I should also do that.
Sir.
1 second. I'll close the presentation mode. Okay. 1 second. How do I do that?
Dr. Shiv Prasad, sir.
Sir.
Our next speaker, young and talented scientist at CSI or CSIO, Dr. Abhay
sir is waiting. Yes.
Is with us, sir. Please.
Sir, welcome, sir. Dr. Abhay Session, sir. Welcome, sir. Welcome.
Thank you, sir.
Sir, welcome, sir.
Okay. Yeah, I'll take a leave. Thanks, everyone. Bye.
Yeah. Thank you, Dr. Sriprasad, sir. Sriprasad, sir. Once again, thank you very much, sir.
Thank you. Okay. Bye.
So now I invite Mrs. E. Manamma to read the brief profile about the next speaker, Dr. Abhay Sachidev, sir, is a CSIO, Chandigarh, sir. So I'll invite Manamma. Please.
Good afternoon. Myself, Manama, Assistant Professor of ECE, respected faculty members and research scholars. Today is the second day of their 3-day FDP on emerging trends in electronics and computer engineering, organized by ECE department in NSRIT. I am so excited to introduce our resource person, Honorable Dr. Abhay Sachdev. Dr. Abhay Sachdev is working as a scientist in Material Science and Sensor Application Division, CSIO, Chandigarh. He did his PhD in nanotechnology at IIT Roorkee. He did his master's in nanotechnology in IIT Roorkee. His scholastic achievements are: he scored as the second highest CGPA in his master's in IIT Roorkee. He was selected for the award of SERD National Postdoctoral Fellowship in 2017. He is a recipient of SERD Early Career Research Award in 2019. His research areas are biomaterials, nanomaterials, antimicrobials, biosensors, and microfluidics. He has undertaken 7 research projects. In those, 4 were completed and 3 were and ongoing projects. Currently, he is guiding 4 PhD students. He is mentoring one research associate, that is, he is a Dr. Vijayesh Kumar Garu. He guided 8 MTech and MSc students. He published 2 books and 5 book chapters in 36 renewed journal articles, and he is a 2 patents. He delivered 7 invited talks on various applications in nanotechnology. He was attended to 14 conferences and workshops. So I am here welcoming Dr. Abhay Sachdev to give an extraordinary lecture on prospects and applications of nanomedicine. Welcome, sir.
Thank you, madam, for a nice introduction. And let me share the screen. So is my screen visible to all?
Visible, sir.
Okay. Am I audible?
Yes, sir.
Audible,
Okay.
sir, audible.
Okay, okay. So thank you very much. And first of all, I would like to thank the organizers for inviting me to deliver this talk at this FDP program. So the topic of my talk today would be the prospects and application of nanomedicine. So before proceeding further, let me give you a glimpse of my institute as well as myself and explain what all we do and where we come from. So CSIR is a network of around 38 laboratories spread across the country. So CSIO is one of the constituent labs of CSIR, which has the mandate of developing indigenous instrumentation related to the area of strategic healthcare and public safety and agriculture as well. So basically, we also have an academic council of scientific and industrial research, ACSIR, so which undertakes the PhD programs, and also we welcome students to do their dissertation work for MTech and summer training programs. So the overall goal of our institute is to achieve technology self-reliance and high scientific quotient. So I belong to this material science and sensor application division, so which has its own mandates to work on. So it is our division is working on nanomaterials, biotechnology, water pollution, environment, defense and security. So I work on the interface of nanomaterials and biotechnology. So my area of research is nanobiotechnology, nanomaterials, antimicrobials, biosensors and microfluidics. So let us start with the very basic thing, since I feel like you people are from diverse backgrounds. So I don't know whether you are like accustomed with the nanoparticle, nanotechnology. So I'll start from the very basic thing. So first of all, we'll see what is actually a nanoparticle. So nanoparticle is any material. It is the standard definition, which is having at least one of its dimension in the range of 1 to 100 nanometer. So nano, as we say, it is derived from a Greek word nanos, means dwarf or small. So Norio Taniguchi in 1974, he coined the term nanotechnology. So a nanometer, you can like visualize it to be 1 billionth of a meter. So 1 meter distance, you can, as we are sitting here, you can see it would be around the distance from the tip of your nose to the hand. So imagine how small is the nanoscale in which like the various technologies, devices are being developed these days. So let us visualize how the nanoscale looks in comparison to macro. So macro scale, if you see a person, if we see him in the nanoscale, it is around 2 billion nanometer the size. Apple 8 centimeter in size, it is around 80 million nanometer. Similarly, micro range, your hair falls in the micro range, your eyes are in the micro range. Again, E. coli bacteria, it's 5 to 20 nanometer. Then comes the nanoscale, in which you are synthesizing the nanoparticles and you have the chemical elements present in the nano range, like the hydrogen atom, the size is around 1.1 nanometer. So macro you can visualize by your eyes. So your eyes have a very good like resolution. It is around 576 pixels. So your eyes can visualize the macro scale objects, while for visualizing the micron scale objects, you need a light microscope. So light microscope can visualize your like objects in the range of microns. While for visualizing the things in the nano range, you need to have advanced instrumentation imaging facilities, which we'll be discussing in the future slides. So imagine like if I will say, like if we are all the persons on this planet, they become nano. So imagine they would all would be like accommodated inside a simple Hot Wheels car, the toy car. So imagine how super tiny the nano is. So another few examples of the nano range are your viruses, your cell structures, then your RBCs. So these are some other examples of the nano range materials and devices. So simple example is we and you are nano in comparison to the billion population of the India. And 1 rupee note, if you see, it is nano in comparison to 100 crore, but it still has a value. So these nanoparticles, we can visualize them through advanced imaging techniques, I have said. These are the transmission electron microscopy and scanning electron microscopy. So using these techniques, you can actually go down till the 2 nanometer to 20 nanometer range. And then you can visualize these nice nanoparticles with different shapes, sizes, as well as you can determine their composition as well. So coming to the nanoscience and nanotechnology, nanoscience is actually the study of nanomaterials, their properties, and the related phenomena. While nanotechnology, we say it is the application of nanoscience to produce the products as well as devices. So let me share a very simple example to you to visualize the power of nanotechnology and how nanoscience is related to nanotechnology. So quantum dots, these are actually human-made semiconductor nanoparticles, which are less than 10 nanometer in size. So these quantum dots, as you can see in this pic as well, they have a property of fluorescence. That is, if you shine some light on them, so based on their size, they will give some different colors, and they will give very nice, different, beautiful colors due to their inherent property. Okay. So what this quantum dot have done, they have given rise to the quantum dot LED TVs. You might have gone to the market and saw new TVs coming up there. And the salesperson explaining to you, like, sir, take this TV. It's a slim quantum dot TV. It has good color technology and all. So the basic of this goes to the nanoscience. The credit goes to the nanoscience. So what the Samsung and other companies have done, they have taken these quantum dots and embedded them into the form of a film, and they sandwich this film into the panel and the LED backlight. So whatever the LED backlight it is coming from the back end, it passes through the quantum dot enhancement film and it passes through the LCD panel, which gives rise to very beautiful colors and pictures on your screen with very beautiful like pixel quality as well, which will not get in normal HDR or maybe 4K technology. You'll not get. So this is all due to the quantum dot enhancement color effect. So this is the one example where like the nanoscience has given rise to the nano product, product based on nanotechnology. Okay, so moving on further. So nano, the inspiration comes from the nature as well. So the we can take the example of gecko feet. So gecko is actually a lizard which are very good, considered as very good climbers. So when you analyze these geckos, so you see like they have nano-sized hairs on their feet that use intermolecular forces, to be precise, van der Waals forces, allowing the lizards to stick firmly to surfaces. So like a closer examination of the gecko adhesive system, it leads to the like analysis like the mesoscale. You can see the structures in the mesoscale, while the microscale you see the more clearer structures in that. So when you go to the nanoscale through the transmission electron microscope, you will see an array of vertically aligned structures. So these structures are basically responsible for adhesive nature. So just imagine how much adhesive is its like nature. So a gecko can lift up to 130 kg of its weight. So based on this like concept, what the researchers have done, they have developed a gecko tape. So this tape can hold up to 1 kg of the weight. It is very small, very thin, but see the power, like it can hold up to 1 kg of the weight of the thing. So it can be used for the weightlifting applications. So another thing which the researchers have done, so taking a leaf out of the biomimicry, what they have done, they have started making use of these nanostructures which are found in the setae of the GECO to improve the grip of shoes that can be used during mountaineering, so that one does not slip or like fall during ascending or descending. Another example I want to share is the lotus leaf effect. So there are certain leaves, they have a particular surface structure that makes them difficult to get wet. So as soon as the water falls on these leaves, it curls up into little droplets due to the nano-sized ridges as well as wax-coated hairs. So this phenomena we call as the lotus effect. So taking inspiration from the nature, we call it as biomimicry. We are trying to mimic the nature. So engineers are trying to make clothing that can protect you from the stains. So what they have done, they have developed super hydrophobic coated cloths which can be used as a dirt repellent, and something, if something falls on your shirt during some party or something, so these clothes are already in the market. I want to tell you that as well. So if something falls on your shirt, so due to the super hydrophobic nature of these cloths, your clothes will not get dirty and it will be eliminated as soon as it gets onto your shirt. So that is the power of the super hydrophobic coatings on these shirts. So basically, nano has already penetrated in our everyday life. So the future, like in future, we might see a nano supermarket in which we can see products related to various diverse areas like cosmetics, paints, security, forensic, every different area, food security as well. You name it, and you will find the nano related products in your market shelves. But the products which are already available in the market, I want to discuss that as well. So nano titanium oxide based paints are used as self cleaning surfaces. They are very good hydrophobicity, so that is why they are being used in paints. Then another good invention of the nanomaterials is the use of carbon nanotube body armor as a bulletproof material. So like the steel is very heavy to wear, and as well as if the accidentally you get hit by a bullet, if the soldier gets hit by a bullet, so the impact would be as such like the person would be thrown at a distance. While these carbon nanotube body armor bullets, they absorb all the impact, and as well as they are very light to wear because they are, see, it is in the nano range. It is very small, very light to wear as well. Then another example is the Tata Chemicals, which have manufactured Tata Swatch using the silver nanotechnology. So they have actually incorporated silver nanoparticles inside one of their filters for removing the viruses, bacteria, and other organic matter inside the water and enable clean drinking water. So, and there are like certain sunscreens as well, which are made up of zinc oxide nanoparticles. This is one of the earliest examples of nanotechnology based products. So these zinc oxide nanoparticles, they absorb the harmful UV rays and they protect your skin from burns or like harmful effects of UV. Then in skincare products, your antiseptic creams, you can find nano silver, which have very good healing properties. So if you get burns, so this nano silver based cream, you can see burn heal or real heal. By these product name it goes. So these creams contain nano silver and they have very good healing properties. Then you have nano composite based scratch resistant coatings. So there are certain nano composite combination of 2 or 3 nanomaterials which prevent the scratching of the surfaces. So for these designer glasses and goggles, so people have coated those nano composites onto these glasses to enable scratch resistant products. Then now we'll discuss what are the actually the properties that give rise to the different phenomena of the nanomaterials. So over the years, the researchers have done a lot of basic science research to determine the properties of nanomaterial. And these properties can be narrowed down mainly into 2 things. So the properties can be different at the nanoscale due to 2 main reasons. First, the very basic reason, nanomaterials have a large surface area to volume ratio. which makes them more chemically reactive and affect their strength as well as electrical properties. The second one being the quantum effects. So those like who have studied some basic physics as well, so they might be knowing like as soon as you go to the nanoscale, these quantum effects come into play and they dominate the behavior of matter at the nanoscale. So the bulk material, if we see, it should have constant physical properties regardless of its size. But as you move to the nanoscale, so at each and every size range, you get different properties. So this will be discussing in the further slides as well. And another phenomena for the quantum effects leads to the size dependent properties, such as in the semiconductor particles and superparamagnetism in magnetic materials. So origin of the properties can be basically explained by this figure. So you can see in bulk metal, your conduction band and valence band are very nicely overlapping with each other, and there is no free electron motion. So electrons are very much confined. While when you decrease the size, your separation between the valence and the conduction band increases. So there gives the chance to the electron, this gives a chance to the electron to move from the valence to the conduction band and then come back to the valence band and for to and fro motion. And the quantization sets in. Quantization is nothing but you can see the separation of the levels. So this is actually the quantization. Your bands are no longer continuous. It is like separated from each other. So this gives rise to the most of the different properties of these nanomaterials. So nanomaterial properties, they basically depend on the crystal structure and size. So if you take the example of physical properties, the melting point decreases with decrease in size. Then comes the magnetic properties. So in the range of nanoscale, the magnetic material has a single magnetic domain. So it is not composed of multiple domains. It has a single magnetic domain, which can randomly flip in response to the external magnetic field, leading to various applications like supercooling effects, superconductor effects. So these are a few of the effects of the nanoparticles. Then comes the optical properties, which influence the light absorption effects. Then thermal properties, then nanocrystalline materials are usually have a low thermal conductivity when compared to their bulk constituents. Catalytic activity, obviously, as I say, their reactivity increases at the nanoscale, so they can be efficient catalysts in many reactions. Then electrical properties are also one of the important properties. So nanomaterials, they usually exhibit electrical properties in between semiconductors and metals, depending on the diameter of the molecules. So the simple example for this being like carbon is there. Carbon, if you take, it is a black amorphous material with no fascinating properties. But if you see the allotropes of carbon like graphene, CNTs, they are very good conductors of electricity. And that is the reason they find like applications in various areas like sensors, energy storage, etc. So as I was saying, like material properties, they vary with size. So this is a simple example which will give you an idea to how the properties change, which will be you'll be able to visualize how properties change with size. So the bulk gold film, as you can see, so in the ornamental form, as you have seen as well, it is like yellow in color. So as soon as you reduce the particle size to 30 to 500 nanometer, you'll get a crimson to blue color particles in nature. So once you decrease the size more, it will be little red metallic in nature. So you further decrease the size to 1 nanometer, it will become orange. So that is the size effect which you see visually in the solutions. So that is the reason like bulk gold does not have any catalytic activity, while the nanoparticle of the gold has very excellent low temperature catalytic properties. So this optical property of the nanomaterials, that is the absorption and fluorescence, we'll see. So you can see like the gold and silver have distinct colors due to the phenomena known as plasmon absorbance. So this phenomena happens when your incident light, it creates oscillation in the conduction band electrons on the surface of particles. So let's see the example of 30 nanometer, 24 to 30 nanometer particles. So the SPR band, the absorption band for these particles lies in the blue-green region of the EM spectrum. So they absorb the 450 nanometer light, while transmitting, they emit the red light, yielding a rich red color. So similarly, for larger particles, you can see the 90 nanometer particles you can see on your figure on the screen. So they are actually purple in color. The reason being, your larger particles, the SPR band shifts to the red region. So in that case, your particles absorb the red light and they emit the purple light, the reverse case. And similarly, the band gap also depends on the particle size. So you can see, like, this is the fluorescence effect in the nanoparticles. So the smaller nanoparticles will give some cyan color fluorescence, while the larger particles will give some red color fluorescence. So you can ascertain the one which is giving cyan color fluorescence is having low particle size, while the one which is giving red color fluorescence is having the more particle size. So nanotechnology is actually not new. We have been researching for years, but even in ancient times, you can find various instances where people have used nanoparticles and nanotechnology has been there. But obviously at that time, the science was not that much advanced, like people could ascertain the reason why is it happening. But now the nanotechnology science has matured so much, like we can figure out what is the exact phenomena happening. So 1,000 years ago, Chinese used gold nanoparticles as an inorganic dye to introduce red color into ceramic porcelains. And in 1857, Faraday prepared gold colloids that was stable for almost a century before being destroyed during the World War II. And while some of you might have visited churches, so medieval churches, so their glasses are very fancy. The glasses are very good in color. They have mixed mosaic of glasses. It is only due to the fact, like, they are actually composed of fusion of gold and silver nanoparticles in the glass. So gold and silver nanoparticles have different colors at different sizes. So when they form a mosaic, they give rise to these beautiful patterns in the medieval churches. So it is actually due to the nanoparticle size effect. Another example being the Lycurgus cup, which is one of the oldest synthetic nanomaterials. So it gives two colors, that is the dichroism, due to the presence of nanoparticles within the range of 50 to 100 nanometer. So these, what is this effect due to? These nanoparticles, they give it different color in different lights. So this cup is red in transmitted light, while it appears green in scattered light. So red color is due to the absorption of the bigger particles, as we have seen in lab-based nanoparticles as well, while the green color is attributed to the light scattering by colloidal dispersions of silver nanoparticles with size range greater than 40 nanometer. So this dichroic effect is due to the dispersion of gold and silver nanoparticles. Then we'll come to the different type of nanomaterials that exist. So the first one are the naturally occurring nanomaterials. So why we call them naturally occurring? The reason being, they are produced as a result of various geochemical processes or biomechanical processes. So these nanoparticles are present inside your forest fires, your sea sprays, your mineral composites, your volcanic ash, and your viruses. Like, these are the notorious ones, which are disease causing organisms. They are actually the naturally occurring nanomaterials. Then comes the man-made nanomaterials. So man-made nanomaterials are those which we synthesize. Sorry. Yeah. So man-made nanomaterials are those which the humans have deliberately synthesized for specific applications. So we categorize the man-made nanomaterials into incidental as well. Incidental means there is indirect or direct human intervention in that. While cooking smoke, most of you would be surprised to know the cooking smoke contains carbon nanoparticles. Same is the case with the diesel exhaust, and then the welding fumes, sandblasting, industrial effluents. So these are the products of human activities which we are doing unconsciously, and we don't know, we are spreading the nanoparticles in the environment. So to give you a more clear idea about it, incidental nanoparticles, they are more variable because they come from various sources, like unconsciously. So they have different size and shapes. They are composed of different elements, while engineered nanoparticles are those which you are actually synthesizing in the labs. So you can select what can be your shell material, what can be your core material, while incidental nanoparticles, you have no control because they are released as a product of the human activities. So engineered nanoparticles, they are more defined in that manner. So example being metal, quantum dots, nanotubes, nanocapsules, etc. So how to make these nanostructures? So there are two approaches, the one being the top-down approach. So top-down approach in layman terms, it means building something by starting with a larger component and carving away the material like a sculpture. So you see, you take a piece of rock, you carve it and make a statue. So same is the case of nanomaterials. You take a bigger material, you etch it in controlled environment and you get the nanoparticles. Another approach is the bottom-up approach. So bottom-up approach is building something by assembling smaller components, like building a car engine, atom by atom assembly. So in nanotechnology, there is a very common way of making it is the self-assembly of atoms and molecules, as we see in the chemical and biological systems. So how to make nanostructures? Well, it entirely depends on what sort of technique you want and what sort of application you are looking at. So you can either go for the top down or you can go for the bottom up approach. So there are various methods, various chemical and physical methods for that. So bottom up approach, there are methods like vapor deposition, sol gel, electrochemical, bioreduction. Then top down, you have mechanical processes like ball milling is there. You mechanically mill the particles and reduce the particle size. Then there are thermal processes. Then optical processes through laser, you are mediating laser ablation and you are ablating smaller particles. Then sputtering or chemical etching is a top down approach. Okay, so we'll come to the next part of this. Nanotechnology and nanomedicine. So nanotechnology has almost spread its influence in various fields, and that is why till date I don't consider nanotechnology as a subject. It is actually a multidisciplinary science which deals with the knowledge of physics, chemistry, science, and other engineering branches like mechanical, civil, and obviously it has application in those branches as well. While nanomedicine, to be very precise, it is actually the application of nanotechnology to achieve innovation in healthcare, and it is also composed of various allied areas. You need to have knowledge of various allied areas to actually work in the area of nanotechnology as well as nanomedicine. So nanomedicine is actually nano in medicine. So nanomedicine basically creates your nanostructures, your nanoproducts, your nano objects that have therapeutic, that is your healing, and secondly means the diagnostic, that is your detection part. That diagnostic and therapeutic abilities by you are exploiting the properties of the nanomaterial and you are reaping the medical benefits. So that field is known as nanomedicine. So nanomedicine, it ranges from the medical applications of nanomaterials and biological devices to nanoelectronic biosensors. And because of their small size, these nano devices can very efficiently interact with the cells and can go inside the cells as well. So accordingly, they have the potential to detect the disease as well as deliver the treatment. So nanomedicine is actually divided into 4 areas. First being the diagnostics. So diagnostics are magnetic resonance imaging, positron emission tomography. So in these things, so nanoparticles are being used as the contrast agents as well as the amplifying signal elements. So you have the gadolinium nanoparticles, they create the contrast in the MRI. And then you have the therapeutics. So therapeutics comes the nanoparticles in the cancer therapy. Then your antimicrobial nanoparticles. So wherever you need to let's say you want to create antimicrobial food coatings. So there lies the need of the antimicrobial nanoparticles. Then you have nanoparticles in cancer therapy for treatment as well as diagnosis of cancer. Then nanoparticles have been recently used in anti-diabetic therapy as well. So as we all know, insulin resistance is a big challenge for those suffering from the type 1 diabetes. So researchers have started to make glucose responsive nanoparticles that can initiate the production of insulin inside the body, and the insulin and the sugar levels can be maintained. Then drug delivery systems, you have polymeric nanoparticles, liposomes, different type of nanoparticles. Then another good area of research is the regenerative medicine. So regenerative medicine, you are actually blending your scaffold, cells, nanomaterials, and other biological factors to create cells, tissues, and then maybe organs artificially, and then implanting them inside the body to initiate their growth and repair the damaged tissues or organs. So there also is application. So I have underlined, I have encircled these vaccines. So recently the vaccines has been a new addition to the nanomedicine. So I will share some interesting aspects with you in further slides regarding vaccine. So now there are not 4, there are actually 5 areas of nanomedicine research. So playing with nanoparticles for disease diagnosis and therapy has been the core of this nanomedicine. So is personalized approach via nanoparticles achievable? The answer is yes. So you can design nanoparticles in the range of 1 to 100 nanometer, and you can have a variety of nanomaterials like polymers, metal, carbon nanotube, lipid based nanoparticles. You can make various shapes depending on what sort of application you want, what sort of activity you want. And then comes the surface. You can modify the surfaces, you can modify the surface charge with specific functional groups so that your nanoparticle behaves in a manner in which you want it to behave. So I'll be sharing a few case studies related to the nanomedicine. Okay, so bhasmas, if somebody has interest in the medieval science, so they are these days, I've read a few reports, they are considered as the nanomedicine of ancient times. I was also surprised to know about this fact. So bhasma is actually an Ayurvedic metallic mineral preparation, which is well known in the Indian subcontinent since 7th century AD. And it is widely recommended for treatment of many disease conditions. So bhasmas are actually claimed to be biologically produced nanoparticles. Swan bhasma specifically, if you see, it has been characterized as globular particles of gold synthesized at high temperature. So when this Swan bhasma was analyzed under an electron microscope, so what the researchers ascertained, they could find similar nanocrystalline materials which possess similar physico-chemical properties compared to the gold nanoparticles. So they went a step ahead and studied and ascertained like the therapeutic effect of bhasma. It is attributed to the large surface area of the nanocrystalline materials and small particle size by which they can be easily transported inside the cell and to specific target size as desired. Then comes the science fiction. It is no longer, nanorobots are no longer the science fiction now. They earlier used to be. So on your screens, you can see a robot swimming inside your arteries and veins using a pair of tail appendages. So this inspiration has been drawn from the structure of E. coli bacterium you can see on your screen. So what the researchers have done, they have created a nanorobot. It has a swimming tail, so it swims through your blood in the arteries and veins. It has a capacitor, so capacitor gives the energy, provides the energy for like traversing through the blood stream. Then it has the payload. So payload means any drug or any therapeutic molecule which you want to deliver inside the cells. Then it has a micro camera. So camera needs to track the movement of this nanorobot inside the body. So how this stuff works, actually, you might be comprehending this thing like it does not only require the knowledge of biology, it requires the knowledge of electronics, it requires the knowledge of medicine, it requires the knowledge of biology, chemistry, and even energy related applications as well. So that is why I say like nanotechnology, nanomedicine, everything is interdisciplinary in nature. So nanotechnology for cancer therapy, as you can see on the right side of picture. So traditional drugs, if you if you are giving in the body in the form of chemotherapy, it's a very common therapy for treating the cancer. So they will spread throughout your body. While nanoparticles, you can visualize in the picture, wherever you want the nanoparticles to go into the body, you can do with that. While it is not possible with the conventional chemotherapy. So the key benefits of nanoparticles for cancer therapy are, it provides multiple functionality, like you can control its targeting, you can control the delivery, reporting, improved therapeutic index. So supposingly you want the like drug inside the lungs only. So you whatever doses you want inside the lungs, you will be specifically able to deliver those doses inside the lungs only, and they will not go to the liver, to the kidney, or to the heart. So through nanoparticles, you can deliver the drugs directly to the lungs. And obviously, if they are not spreading in the body, obviously the toxic side effects are going to reduce. And another important thing, like nanoparticle, obviously they can accommodate large quantity of drugs. You can go for multiple drug delivery as well to the tumor site. You can go for nucleic acid delivery as well. And obviously nanoparticles have like heating and other physicochemical properties which can be used for the non-drug therapies. So this is one simple example in which you can see the traditional treatment when you give the drugs to these cells. So what happens? So drug does not know like this is a healthy cell and this is a cancerous cell. So what happens? Drug randomly kills the cancer as well as your non-cancerous cells. While the directed treatment using the nanoparticles, you are directly giving the nanoparticles to the cancer cells only, and your non-cancerous cells are actually intact in nature. So that's the power of nanotechnology for cancer. So in one of my works, I had the opportunity to design some multifunctional nanoparticles for cancer therapy. So these nanoparticles were able to give fluorescence as well as they were able to mediate the cell death, as you can see on this screen. So the nanoparticles were composed of carbon dots. These were actually the fluorescent nanomaterials, and the silver zinc oxide nanocomposite, it was actually the one which was specifically targeting the cancer cells and killing them. So another interesting aspect I want to share is the photothermal therapy for cancer. So nanoshells have actually metallic outer layer and a silicon core. So these nanoshells made of gold have a special property. So nanoshells, they can be irradiated with the near infrared light. So I hope everybody knows when you shine some IR light, so the particles will absorb some heat and they will heat up. So what happens using the similar concept, the researchers have incorporated these nanoshells inside the cancerous cells, and externally when they shine the light on these nanoshells, they light up and they become hot. They raise the temperature to like 80-90 degree, not 80-90, sorry, 70-80 degrees centigrade inside the body. So that temperature is sufficient to destroy the cancer cells. So you have the directed delivery as well, and then you have the therapeutic response as well. So coming to the commercial aspect, so I'll explain, like it is not related to the research. So you will find nano related products in the for cancer therapy in the market as well. Very good example for this is the Abraxane. So Abraxane is actually the paclitaxel drug. It is a chemotherapeutic drug which is sold by the name Taxol. So this Abraxane, what they have done, they have taken albumin nanoparticles, they have conjugated paclitaxel with it, and then they have made a dispersion of it, which got the FDA approval for treatment of metastatic breast cancer. And another interesting case study is the nanobots for breaking the kidney stones. So kidney stones are actually intensely painful. The larger the stone is present, the more difficult it is to pass through the urine. So there are various procedures like ultrasonic frequencies, like doctors use these days, but it is always not effective. So another way the researchers have taken this up is like they have taken a nano robot which can carry actually the ultrasound shock waves directly to the kidney stones, so that the large kidney stones can be broken into smaller pieces which can be thrown out of the body. Or like another way it can be, you can target the nano robots inside the kidney cells and shine the laser light on them, so it can also break down the bigger stones into smaller particles, and so that they can be eliminated. So another example of nanoparticles in the nano drug delivery system is the treatment of arthritis. So arthritis is actually a very painful joint disease in which your bones and cartilage get inflamed and like the person feels pain a lot. So what the researchers have done, they have synthesized magnetic nanoparticles loaded with the anti-inflammatory drugs. So what they do, they inject the drugs through the muscle. They inject the magnetic nanoparticle drug conjugate through the muscle, and through the help of the external magnet, they drag it to the site of the joint. Like this joint, you can see in the picture, it is actually the joint between your upper bone leg and lower bone leg. So through this external magnetic field, they are able to retrieve the nanoparticles to the site of inflammation. Another strategy is the like incorporation of dextrin sulfate nanoparticles. So what they have done, dextrin sulfate is being given for reducing the inflammation of the joints. So what people have done, they have made a nano formulation of the dextrin sulfate, and they have modified it with some receptor so that it goes to the targeted site, that is your joints only, and then it releases your dextrin sulfate nanoparticles for alleviating the pain symptoms. So in future, we might see a mouthwash full of smart nanorobots. Sounds interesting. So in future, you might see like these days, like if you brush the teeth, there will always be some areas in which the bristles will not go. So nanorobots, just imagine, they can go and do deep cleaning of your teeth. So you can have a mouthwash which can be composed of nanorobots. So whatever the companies claim, like it can remove 99.9% of the germs. So this is just a tagline these days. So maybe in future, through the help of nanorobots, we will be able to achieve actually this target. Then nanomaterials have been used for 3D organ printing. So 3D organ printing is actually very interesting field in which one can actually print an organ in the lab. So everyone of you might have used those printers for printing the paper. So it is synonymous to that. In that case, the cartridge is composed of bio inks. So in normal printer, it is a different ink. This printer also has a cartridge which is composed of bio inks. So through that, you can actually create an artificial organ using a 3D printer. So in 2019, there were some Israeli researchers which actually created a fully functional heart on using a 3D printer. So that was one of the groundbreaking research in this field. And using the nanomaterials in the with the implant with the this 3D printed materials, one can enhance their physical behavior by the incorporation of various type of nanomaterials, nanoparticles, crystals, fibers. So when you combine nanomaterials with these bio inks, it becomes nanobio inks. So in one of the studies, what the researchers did, they made a nanocomposite hydrogels containing nanosilicon, which promoted the formation of complex bone structures. So just imagine if the person, some person is having a, like his bone is gone beyond repair. So you can artificially create these structures outside the lab and then implant inside the body. You are actually doing what you are doing a regenerative engineering. So you are actually regenerating the part of the bone artificially and then putting it inside the body, and body's internal physiological mechanism can help it get bond to the existing structure as well as grow it. So COVID-19 has been an unprecedented pandemic for all of us during the past 2 years, and we are still struggling to overcome it. So during the pandemic, there were various nanotechnology based strategies. So we call them as nanotechnology toolkit, for which basically meant for the protection, diagnosis and treatment of the COVID-19. So we'll discuss each one of them now. So first of all is the COVID-19 protection tools, nano tools. So under this, what the various researchers around the world have done, they have created antiviral PPEs, personal protective equipment, to counteract the pandemic. So in one of the works, what the researchers did, they created a super hydrophobic antimicrobial mask by depositing 2 layers of nanoparticles of silver as well as graphene onto N95 respirators. So N95 mask they took, they modified, as you can see in this picture as well, they modified it with graphene and silver nanoparticles. So when they shine the light on these masks, so what happened? It reached the temperature of 80 degrees centigrade within 1 minute. So at that temperature, SARS-CoV-2 virus, the studies have shown it gets deactivated at 56. So this mask was able to generate temperatures around 80 degrees centigrade. And one more important thing I want to share, like this mask is like, it is a multi-layer one, so you'll not feel the temperature when you wear it. So if one goes into the sunlight, so sunlight can easily like enhance the temperature of this mask and mediate antiviral effect. So in another work, the normal surgical mask, which everybody might have worn during the COVID pandemic. So what the researchers did, they modified this mask with an additional layer of molybdenum disulfide nanosheets. So they sandwiched this layer between your hydrophobic layer as well as your soft absorbing layer. So they sandwiched this layer, and what they observed, like the photothermal properties, like they observed when they when they went for the trial, they saw like this fabric reached up to 77 degrees centigrade temperature within 3 minutes of exposure to the sunlight. So these were some groundbreaking works related to nanotechnology for COVID-19 prevention. Then comes the COVID-19 diagnosis. So COVID-19 diagnosis based on the different nanoparticles. So they have been categorized into different assay principles. So the first one being the colorimetric assays and fluorescent assays, where the nanoparticles have been employed as signal amplifiers as well as visual signal interpretation. While the SPR and electrochemical assays, they have utilized the dimensionality of the nanoparticles, and then they have used it for various optoelectronic properties for sensing applications. So in this thing, like for developing these kind of assays, you have your various targets, like either you take the RNA for detection, or you take the proteins for detection, or you take the immunoglobulins, that is the antibody for a layman. Antibody, I hope everybody understands. So these are the targets for detection of COVID-19 using the nanoparticles. So as we all know, like RT-PCR was the most common test in these times, but it is considered as a gold standard as well, means like it is the benchmark for all the test samples. But they have their own share of problems. Like supposingly, if somebody went for a RT-PCR test, he would get the report to 24 to 48 hours. And RT-PCR, most of you might have felt like it has to be performed in specialized laboratories by skilled personnel only. So here comes the innovation of the nanotechnology. So nanotechnology based diagnostics, they are highly sensitive compared to conventional techniques, in that they can detect extremely low quantities of pathogens, that is your virus, in short time, sometimes even before the symptoms start appearing. So as an example, I have shown here, like there was one lateral flow assay based on based on gold nanoparticles for COVID-19 detection. So as you can see in this picture, it is what you can see at in the A part, it is actually a paper based membrane which has been compartmentalized into 4 sections: sample pad, conjugation, test zone, and the absorption pad. So in the sample part, in the sample pad, you take the sample from the patient, you put it there. So through the capillary action on the surface of paper, the sample flows to the conjugation pad. So on the conjugation pad, you have your gold nanoparticle antigen conjugates. So they interact with the antibodies present in the patient sample, and they give rise to a signal. Further, to enhance the selectivity and accuracy of this test, the confirmatory lines are the lies in the test zone. So the researchers selected actually 2 antibodies, IgG and IgM. So they are actually indicators of your COVID-19 infection. So if the antibodies are present in the sample, they will bind to the IgG, to the M line as well as the G line, while the control line remains the same for the positive as well as the negative sample. So based on this antigen antibody interaction, so we can interpret the results as shown below. So C means the control line. So control you will get in all patient samples, those who are having COVID or those who don't have. But those patients who have COVID, they give rise to IgM line, IgG line. And if you get both the lines, that means your time is up. You have contracted the COVID. So that is why they have used 2 type of antibodies, so that to be double sure about it. Okay, so now I'll come to the final part of it. So for vaccine development also, researchers have done a lot of research for creating mRNA based vaccines. So Moderna and Pfizer vaccines have actually nanoparticles. So it is very surprising to know. So what they have done, they have encapsulated this mRNA. mRNA is nothing but like a spike. It encodes for a spike protein related to COVID-19. So vaccine is one thing which gives you artificial immunity against the virus. So once you how does it happen? Let me explain. So you take a muscle shot of the vaccine to your muscle. So through the muscle, the mRNA enters your cell and it starts making the protein. So these proteins are recognized by your immune system and it begins to produce the antibodies. So these antibodies, they protect you from the infection by COVID-19 when it enters your cells. So basically the thing is you already have antibodies related to COVID-19 before you contract it, so that you get a long-term immunity. So what these researchers have done, this mRNA cannot be directly delivered to the body. So what they have done, they have utilized lipid nanoparticles formulation to encapsulate the mRNA payload. So this enables the mRNA to not get degraded and also to directly go inside the cell very safely. So that is the power of nanoparticles, lipid nanoparticles, to safely deliver the mRNA inside the cells and mediate vaccine production. So with this, I come to the end of this lecture. So thank you everyone for your patient listening, and if there are any questions, I will be happy to address.
Sir, amazing, sir. Technically as well as aesthetically, one of the best presentation of on nanotechnology or nanomedicine.
Okay, thank you very much.
Sir, one question. I heard about drug delivery, targeted drug delivery.
Yes, yes.
Curing cancer, okay, sir. How it is possible physiologically you can target particular cell for heal or like that?
Okay, so targeted drug delivery, actually there are certain routes. So targeted drug delivery, you are actually enclosing the drug inside the nanoparticle. So drug, you can say it is in the angstrom range. So nanoparticle 50, 100 nanometer, it can enclose a lot of drug molecules. And the surface of the nanoparticles, you are modifying it with some tumor peptides. So what are these peptides? They are nothing but protein molecules which recognize your specific cancer cells only. So this is one way, like you are able to deliver the nanoparticles directly inside the cell. They will go and fuse with the cells and directly deliver the payload, whatever are the drug molecules inside the cell.
Yes, sir. Yes, sir. And the second question, when man-made nanomaterials, sir.
Yeah.
Suppose you are doing experiment, okay, it is fine. But if we are doing simulation and or like that, how we take material property of nanomaterial? Is it different from bulk? Definitely, sir. Look like.
You are asking like if you are simulating the material properties.
Is material properties are available in literature, or we have to?
Actually, simulation, I don't have any idea. It's a different field of computational nanotechnology. So these all things, whatever are there, they are actually related to like experimental things.
Experimental outcomes.
Yeah, experimental only. So computational, yes, obviously there will be certain like you say boundary conditions and already existing parameters where you can like play around with the material properties.
Yes, sir. Yes. Thank you, sir. Any question or Dr. V.C. Prasad, sir, please?
Any questions from the participants, please? Please get clarify with your doubts. Dr. Ravi, sir, it's a very wonderful session, sir.
Thank you very much.
Very wonderful. I've gone through your bio. Actually, what we have read is a very small thing we have to read.
Okay.
It's extraordinary work you have done till now, and many ongoing projects are also. So, great. Today we had a great day session in the afternoon. And, thank you very much from the Department of Electronics and Communication Engineering, NSRIT. Nedupalli Satyanarayan Raju Institute of Technology, Visakhapatnam, sir. बहुत शुक्रिया जी.
Okay. Thank you very much for the appreciation and patient listening. So
yeah, it's very good, sir.
Yeah.
Sir, Picture, sir.
Oh.
Camera switch on.
I request all the members to please switch on the cameras once. Sir, could you please switch on the cameras once for a group pic? I request all the members. Request the members to please switch on the camera for a second. Thank you. Thank you for today. Virender, continue the vote of thanks.
Yes, sir. Okay, Dr. Abheshdev sir, thank you very much for this beautiful lecture. You are still here, sir?
Yeah, I'm still online. Yes.
Okay, sir. बहुत धन्यवाद sir.
Oh, thank you very much.
और यहाँ तेलुगु में धन्यवाद को बोलते हैं सर धन्यवादालु.
Oh, nice word I learned today.
This extension of Sanskrit like that.
Okay,
sir. बहुत अच्छा लगा सर और आपकी बैकग्राउंड देख के मुझे CSIO की याद आ गई.
Okay. Anytime you can visit CSIO.
Sure, sir. With HOD sir, we will try to visit Chandigarh.
Yes. Anytime.
Okay, thank you, sir. Thank you very much.
Thank you. I'll leave this meeting.
Definitely, sir. Thank you very much, sir. Thank you.
Dear participant, please fill the feedback form, and with for this session as well as of the previous session, link is available here. Let me check. Fill the
available.
I think, sir.
It's available. Sultan, the same thing you post in our WhatsApp group also. Let the people fill.
Okay, sir. Okay.
So thank you all the participants for your patient listening and support from morning till now. And tomorrow the session starts at 1:30 p.m. afternoon. So 3 sessions along with the valedictory starts at 1:30 to 2:30. Mr. Ayan Karmakar, a senior scientist, Semiconductor Laboratory, Mohali. So he's going to talk about MEMS here. And then the session 2, 2:30 to 3:30, Professor Jafar Ali Khan Muhammad from IIT Hyderabad will talk about signal processing for 6G. And session 3, it starts at 3:30 to 4:30. Dr. Virender Singh, NSRIT, will talk about research proposal writing. So with that, I will close the 3-day FDP with the session 4 from 4:30 to 5.